What if everything we thought we knew about the universe was wrong? Scientists stumbled upon a discovery so strange, so unexpected, it's forcing us to rethink the very fabric of reality. Galaxies, dark matter, the laws of physics, nothing may be as it seems. Today, we're diving into the accidental breakthrough that's shaking the foundations of science. What science thought the universe was. For centuries, humans have stared at the cosmic, wondering not just what's out there, but how it all began and where it might be headed. For the last 100 years, science has given us a story that seemed almost too perfect to be true. It is called the Standard Model of Cosmology, or Lambda CDM, a framework that stitches together the birth of the universe, the formation of galaxies, the dance of stars, and the invisible forces that pull it all together. It tells us a universe we thought we understood, neat, predictable, and elegant. But the deeper we peer into the cosmos, the more we realize the universe might have been hiding secrets from us all along. In the 1920s, a man named Edwin Hubble looked through a telescope at faint, distant galaxies, points of light barely distinguishable from the darkness. And what he saw changed everything. Hubble noticed that nearly every galaxy he studied was moving away from us, and not just a little. The farther the galaxy, the faster it receded. This was not a universe frozen in time, as people had assumed for centuries. It was alive, expanding, stretching itself in every direction. Space itself was growing, carrying galaxies along like leaves on a rising tide. This was the birth of the expanding universe, a revelation so profound it rewrote our understanding of existence itself. If galaxies are flying apart now, logic dictates that they must have been closer together in the past. Rewind the cosmic clock, and the universe collapses to a single, unimaginably dense point. From that singularity, everything, matter, energy, space, and time, erupted outward. This was the Big Bang, the violent yet beautiful beginning of everything we know. The Big Bang framework paints a picture of a universe that evolves with both precision and chaos. In the first seconds after the explosion, the universe was a boiling plasma of particles, radiation so intense that light could not yet escape. Within minutes, the first nuclei formed in a process known as primordial nucleosynthesis, creating hydrogen, helium, and trace amounts of lithium, the building blocks for all matter to come. For hundreds of millions of years, the cosmos remained dark, a vast sea of gas and particles, until gravity began to weave the first structures. Clouds of hydrogen collapsed, forming the earliest stars. These stars ignited nuclear furnaces, producing heavier elements that would one day form planets, oceans, and life itself. For decades, this framework seemed to hold true. The discovery of the cosmic microwave background, CMB, in 1965, the faint afterglow of the Big Bang, seemed to confirm it with near-perfect precision. The universe was hot, it expanded, and it cooled, just as predicted. But even within this triumph, scientists began to notice puzzles, faint whispers of anomalies that hinted the story was incomplete. One of the first and most perplexing mysteries came from galaxies themselves. As astronomers studied how stars rotate within galaxies, they noticed something strange. The outer stars moved far faster than they should, given the visible matter in the galaxy. There simply wasn't enough mass to keep them from flying off into space. To account for this, scientists hypothesized the existence of an invisible substance, dark matter. It was everywhere, shaping galaxies, holding clusters together, yet utterly undetectable. You could not see it, touch it, or photograph it. Its presence was inferred only through gravity, a ghostly architect of the cosmos. And if dark matter was mysterious, dark energy was even stranger. In the late 1990s, astronomers observed that the universe's expansion was not slowing down under the pull of gravity, as expected, but accelerating. Something invisible, something fundamental, was pushing the cosmos apart. Dark energy, represented by the Greek letter lambda in Lambda CDM, became the dominant force of the universe, a driving hand behind a cosmic acceleration we cannot yet explain. Together, dark matter and dark energy make up roughly 95% of the universe, leaving the ordinary matter we know, stars, planets, gas, dust, and humans, as just a tiny fraction of the cosmic puzzle. Lambda CDM worked in astonishing ways. Satellites like WMAP and Planck mapped the CMB with exquisite precision, and the results lined up almost perfectly with the predictions of the model. Supercomputer simulations, when fed with dark matter and dark energy, reproduced the vast cosmic web, the filaments and voids of galaxies stretching billions of light years, almost indistinguishable from reality. It was a model that explained the past, predicted the present, and could even hint at the future. Yet even in its brilliance, cracks began to appear. While Lambda CDM provided a skeleton for cosmic evolution, it relied on invisible components that had never been directly detected. Decades of experiments searching for dark matter particles have come up empty-handed, and dark energy remains a placeholder for a force we cannot measure directly, only infer. Beyond this, precision observations revealed subtle tensions. The Hubble constant, the rate at which the universe expands, did not match when measured using different methods. Measurements from the early universe via the CMB disagreed with observations of the nearby universe via supernovae and galaxies. The difference is small, but statistically impossible if Lambda CDM were complete. And then there were the large-scale anomalies. The universe, according to the model, should be isotropic and homogeneous. Essentially, the same everywhere when viewed on a large enough scale. Yet faint patterns in the CMB, vast structures that stretch across billions of light years, and the sudden appearance of mature galaxies in the first billion years of cosmic history suggested the universe is far more complicated, far less predictable than the standard model allows. Early galaxies were forming stars at rates far higher than predicted. Structures were more massive and organized than expected, and the cosmic timeline of formation began to unravel. In the world of physics, Lambda CDM was elegant, yes, but it relied on assumptions that could not yet be fully verified. Its triumphs are undeniable, a framework that explains the structure of the universe, the distribution of galaxies, and the afterglow of the Big Bang. But its failures are equally stark. Subatomic anomalies hint that our understanding of fundamental forces might be incomplete. Measurements of neutrinos and muons suggest that even the rules that govern matter at the tiniest scales may need rewriting. The universe, it seemed, was both predictable and rebellious, yielding precise confirmations in one experiment while defying every expectation in another. Lambda CDM is not wrong. It is the best tool scientists have ever had for describing the cosmos, but it is provisional, fragile in the face of new data, and vulnerable to surprises. It represents the universe we thought we understood, an expanding, cooling cosmos structured by invisible scaffolds, operating under known physical laws, evolving according to predictable timelines. Yet the deeper scientists look, the more anomalies pile up, the more reality begins to diverge from expectation. The precision era of cosmology. By the late 20th century, cosmology had entered a new age, one where the universe was no longer just observed through the occasional telescope or piecemeal measurement. This was the precision era of cosmology, a period when humanity could finally measure the cosmos with a level of detail that would have seemed impossible even decades earlier. It was a time when the universe began to reveal itself in patterns so intricate, so consistent, that it seemed almost as if we were reading the very blueprint of creation, written in light and gravity. The revolution began with the advent of space-based observatories, instruments that could escape Earth's atmosphere and its distortions, reaching into wavelengths invisible to human eyes. The Hubble Space Telescope, launched in 1990, was the crown jewel of this effort. From its orbit high above the clouds, Hubble could capture galaxies and nebulae with a clarity that dwarfed even the largest ground-based telescopes. Its images transformed not only what we saw, but how we thought about the universe. Spiraling galaxies, star-forming regions, and the faint light from the earliest galaxies suddenly became tangible. Hubble was a window into cosmic history, and the data it returned allowed scientists to trace the universe's evolution across billions of years. It was more than just pictures. It was a tool for precision measurement, capable of determining the rate at which the universe expands, estimating the mass of distant galaxies, and detecting subtle distortions in the path of light caused by gravity itself. Alongside Hubble, the Planck satellite launched by the European Space Agency in 2009 brought the early universe into unprecedented focus. Planck was designed to measure the cosmic microwave background, CMB, the faint afterglow of the Big Bang, with unparalleled accuracy. Previous satellites had mapped this radiation in broad strokes, but Planck measured tiny fluctuations in temperature across the entire sky, variations as small as 1 part in a million. These fluctuations were not just statistical noise, they encoded the seeds of all cosmic structure, revealing how matter would clump into galaxies, clusters, and vast filaments spanning billions of light years. With Planck, the universe was no longer a vague, expanding cloud of gas and stars. It was a precisely quantified entity, its age, composition, and geometry calculable to remarkable exactness. Meanwhile, the Gaia mission, launched in 2013, turned its gaze inward to our own Milky Way, charting the positions and motions of over 1 billion stars. Gaia's precision astrometry allowed astronomers to construct a 3-dimensional map of our galaxy, revealing its structure in exquisite detail, tracking its collisions with smaller galaxies, and measuring the gravitational forces shaping every star's orbit. Gaia didn't just map stars, it mapped the invisible, tracing the influence of dark matter and the gravitational architecture underlying the Milky Way. It provided a level of certainty in the local cosmos that had never existed before, a detailed account of our galactic neighborhood with implications for how galaxies evolve across the universe. Adding to this arsenal, the Sloan Digital Sky Survey, SDSS, created the largest 3-dimensional map of the cosmos at that time, surveying millions of galaxies, quasars, and cosmic structures across vast swaths of the sky. SDSS provided a statistical backbone for cosmology, allowing researchers to measure galaxy clustering, map the cosmic web, and test the predictions of the Standard Model with data that stretched from the nearby universe to billions of light years away. Together, these instruments formed a network of observation so comprehensive that cosmologists could measure the universe on scales from individual stars to the largest known structures, all with unmatched precision. With these tools, the universe began to feel almost solved. The age of the universe could be estimated within a fraction of 1 billion years. The relative amounts of ordinary matter, dark matter, and dark energy could be measured with high confidence, and the geometry of space itself appeared to be flat to within a few percent. The cosmic microwave background aligned perfectly with theoretical predictions. Galaxy distributions matched simulations almost exactly. For the first time, cosmologists could point to specific numbers, not just vague descriptions, and claim a level of certainty previously unimaginable. It was as if the universe had submitted itself to a detailed audit, revealing an underlying order that seemed to confirm decades of theory. But even in this era of measurement and certainty, small anomalies began to emerge. Tiny deviations in the CMB, slight inconsistencies in galactic motion, and faint mismatches in the expansion rate hinted that the universe was more complicated than our most precise instruments could yet capture. The precision era gave cosmologists a detailed map, but it also highlighted gaps, places where the universe did not conform neatly to expectation. It set the stage for discoveries that would not just challenge a theory, but shake the foundation of what humanity thought it knew about the cosmos. With Hubble, Planck, Gaia, and SDSS mapping the cosmos in unprecedented detail, the universe began to feel comprehensible in a way it never had before. Cosmologists could now measure not just the positions of galaxies, but the rhythm of cosmic expansion, the relative weight of its components, and the faint imprints of the first instance after the Big Bang. The universe seemed to obey rules, patterns and ratios so precise that it almost felt like a clockwork machine, ticking in perfect accordance with the predictions of theory. The era was exhilarating. Finally, humanity could measure the cosmos with the accuracy of an engineer checking the inner workings of a finely tuned instrument, and the results were astonishingly close to expectations. The data returned by these missions were so detailed, so internally consistent, that it gave cosmologists a rare sense of confidence. From the fluctuations in the cosmic microwave background, measured by Planck, scientists could calculate the universe's age to within a margin of mere tens of millions of years. An almost trivial uncertainty when compared to the 13.8 billion year expanse it described. They could quantify the proportion of ordinary matter, dark matter, and dark energy in ways previously impossible. They could map the large-scale structure of the universe with such fidelity that simulations could be cross-checked against reality, and the matches were uncanny. It was as if the universe had handed us the answers to its most fundamental questions, almost inviting humans to believe that the cosmic puzzle had been solved. Even the most distant galaxies, glimpsed by Hubble and catalogued in SDSS, conformed astonishingly well to theoretical predictions. Simulations of cosmic evolution based on lambda CDM produced clusters, filaments and voids that closely mirrored what astronomers saw. Stars formed at predicted rates, galaxies grew and merged according to the models, and the large-scale distribution of matter traced out the expected cosmic web. Gaia's high-resolution mapping of the Milky Way added yet another layer of precision, showing stellar motions, orbital paths, and tidal streams that aligned with gravitational expectations, revealing a galaxy in perfect mechanical harmony. For a brief, heady moment, it seemed as though cosmology had finally achieved the dream of science, a universe almost entirely predictable, almost entirely understood, almost entirely mapped. The near certainty was not just about raw data, it was about the convergence of independent measurements, distance scales, galaxy distributions, cosmic expansion, and the temperature fluctuations of the CMB all pointed toward a single, coherent narrative. Different instruments operating across vastly different wavelengths and scales were painting the same story. Supernovae measurements of distant galaxies confirmed the accelerating expansion. Planck's microwave maps confirmed the early universe's density and composition. Gaia's stellar cartography confirmed local gravitational architecture. The coherence of these measurements made cosmologists feel that they were not merely observing the universe, they were reading its instruction manual. This confidence also extended to predictive power. Models generated from lambda CDM allowed astronomers to anticipate cosmic phenomena, from the formation of galaxy clusters to the chemical composition of interstellar gas clouds. Predictions about dark matter distributions guided observational campaigns, and the resulting observations validated the models with remarkable accuracy. The standard model of cosmology seemed to hold up under every test, every measurement, every line of data, reinforcing the notion that the universe was orderly, knowable, and fundamentally comprehensible. And yet, even in this period of triumph, the data began to whisper subtle warnings. Tiny anomalies, almost imperceptible at first, appeared across multiple data sets. The rate of cosmic expansion, the so-called Hubble constant, differed depending on how it was measured. Local measurements using Cepheid variables and supernovae returned one value, while measurements inferred from the CMB returned a slightly different number. The discrepancy was small, but statistically significant. A signal that the universe might not be as simple as the standard model suggested. It was a hint that the precision instruments were uncovering something unexpected, something the framework could not yet explain. Further, faint irregularities in the CMB, previously thought to be noise, revealed subtle asymmetries. Cold spots, temperature gradients, and alignments that should have been random appeared in patterns that defied the assumption of isotropy. Observations of early galaxies showed structures far more massive and mature than theory predicted. galaxies that should not exist according to the cosmic timeline established by lambda c/dm. While these anomalies were rare and initially treated as curiosities, the very existence of multiple independent discrepancies hinted that the universe was far more complex than previously imagined. Yet for all its quirks, the precision era gave scientists a sense of cosmic mastery. It allowed them to quantify uncertainty, measure the universe's age, calculate matter densities, and construct a framework that worked on every scale, from the Milky Way's stars to the farthest quasars. It was a triumph of human ingenuity, a period in which the cosmos seemed to bend to the tools and measurements we devised, confirming that for the first time, cosmology was approaching something like completion. There was a palpable excitement in the field, a feeling that with these instruments, we could answer the questions humanity had asked since we first looked up at the night sky. How did the universe begin? What is it made of? How does it evolve? But the universe is never content with certainty. Even as these instruments provided clarity, they also laid bare the universe's subtle defiance, capturing signals, structures, and fluctuations that did not fully conform to expectations. The precision era was not the end of discovery. It was the moment when discovery became unavoidable. The data was precise enough and the universe strange enough that contradictions could no longer be ignored. Cosmology, which for decades had seemed nearly complete, was about to confront anomalies so profound, so unexpected, that the very foundations of the standard model would tremble. The first cracks, the Hubble tension. On the surface, it seems deceptively simple. How fast is the universe expanding? But behind this deceptively straightforward question lies a puzzle that threatens to shake the foundations of cosmology. The universe is expanding. That, at least, has been known since Edwin Hubble first measured the redshift of distant galaxies almost a century ago. But how fast the universe is expanding, quantified as the Hubble constant, has proven surprisingly elusive. In principle, measuring it should be straightforward. Observe distant galaxies, determine their distance, measure how fast they are receding, and divide one by the other. Yet in practice, the universe refuses to cooperate. Different methods, using entirely independent measurements, have produced results that do not overlap, and the discrepancy is far too large to be dismissed as an experimental error. One method involves observing the local universe. Astronomers study stars in nearby galaxies, particularly a type called Cepheid variables, which pulse at precise intervals that reveal their intrinsic brightness. By comparing their true brightness to how bright they appear from Earth, scientists can calculate the distance to these stars with remarkable accuracy. Building on this, researchers measure the speed at which these galaxies are receding, deduced from the redshift of their light. When combined, these measurements yield a value for the Hubble constant. The most careful, painstaking surveys of the local universe, led by teams such as Adam Rees's group using the Hubble Space Telescope, have consistently produced a value of approximately 73 kilometers per second per megaparsec. In other words, for every 3.3 million light-years of distance from Earth, the universe appears to expand 73 kilometers per second faster. Meanwhile, a completely different approach examines the early universe, using the afterglow of the Big Bang, the cosmic microwave background. Satellites such as Planck measure minute fluctuations in the CMB, patterns of temperature and density that encode the expansion history of the cosmos from the first 380,000 years after the Big Bang. By applying the physics of cosmic evolution, including dark matter and dark energy, scientists can calculate what the Hubble constant should be today. Remarkably, these calculations consistently yield a lower value, around 67 kilometers per second per megaparsec. The difference of 6 kilometers per second may sound small, but in terms of precision cosmology, it is colossal. It is a discrepancy that has only grown more statistically significant with each successive measurement, now exceeding a 5 sigma threshold, the point at which scientists consider a result indisputably real. The implications of this mismatch are staggering, and they cannot be ignored. One possibility is that somewhere, something in the measurements is wrong. Perhaps an unknown source of error lurks in the calibration of Cepheid variables, or in the interpretation of CMB fluctuations, or in some subtle bias in how galaxies are selected. But the more astronomers check and recheck, the more the discrepancy stubbornly persists. Each attempt to reconcile the two values only highlights the tension more sharply. The universe, it seems, is giving different answers depending on whether we measure it locally or look back at its infancy. A reality that forces a profound question. Is there something we fundamentally do not understand about how the cosmos evolves over time? If the measurements are not wrong, then the universe itself might be telling a story we have yet to decipher. Perhaps the expansion of the universe has not been uniform, or perhaps some unknown force influenced the early cosmos in ways that alter the relationship between distance and velocity. Dark energy, previously thought to be constant, might have behaved differently in the past. Or perhaps an exotic form of matter, invisible and undetectable until now, affected the growth of structures in the early universe. Every hypothesis is bold, every suggestion radical, because the Hubble tension touches the very foundation of the Big Bang framework and the standard model of cosmology. This tension is more than a mere academic curiosity. It is a cosmic alarm, a signal that the universe is not following the script we thought it had written billions of years ago. It is a crack in the otherwise pristine facade of lambda CDM, small at first glance, but impossible to ignore under the scrutiny of modern instruments. And it is only the beginning. The Hubble tension hints at the possibility that the universe evolved differently than we expect, perhaps in ways that no one could have predicted when the model was first proposed. Each new measurement, each painstaking survey of galaxies and distant light adds to the mystery, painting a picture of a cosmos that is precise yet unpredictable, familiar yet stranger than we dared imagine. Scientists around the world are racing to understand this tension. Teams are developing new methods, from observing distant quasars as cosmic lighthouses to measuring gravitational waves as independent distance indicators, each approach offering a potential window into the expansion history of the universe. Every new technique seems to confirm the divide rather than bridge it, reinforcing the notion that this is not a simple calibration problem, but a profound feature of reality. The Hubble tension has become a central question in modern cosmology. Are we witnessing a flaw in our understanding of fundamental physics, or is the universe revealing a previously hidden layer of its evolution? In laboratories, observatories, and computational centres across the globe, the tension is being treated as a clarion call. It is the kind of anomaly that has historically led to revolutions in physics, small inconsistencies that accumulate until the old model can no longer contain them. The Hubble tension is one of those moments, a subtle yet insistent challenge to the notion that we fully understand the cosmos. And yet, amid the perplexity and uncertainty, there is a thrill, the kind of thrill that comes with standing on the edge of the unknown, realizing that every new measurement might be the first hint of a universe that is far more complex, far more mysterious, and far more astonishing than we ever imagined. Galaxy rotation, early galaxies, CMB anomalies. If the Hubble tension rattles the numbers, the next anomalies shake the very architecture of the cosmos itself. Astronomers, scanning the night sky for decades, began noticing patterns that simply should not exist. The first hints came from the way galaxies spin. Stars within these colossal islands of gas and light do not orbit like planets around a sun. Instead, their velocities defy expectations. According to Newtonian gravity, stars at the edges of galaxies should orbit far slower than those near the center, where most of the visible mass is concentrated. But observations told a different story. Outer stars were moving as fast as those much closer in, racing around the galactic core at velocities that, under known physics, should have flung them into intergalactic space long ago. This wasn't an occasional oddity. It was a universal feature. Spiral galaxies across the cosmos, regardless of size or age, exhibited the same impossible rotation curves. To explain this, scientists proposed a hidden component, dark matter, a mysterious substance that neither emits nor absorbs light, detectable only through its gravitational influence. Dark matter became an essential pillar of the Standard Model, a shadowy glue holding galaxies together. Yet here's the paradox. Decades of experiments, from underground detectors to particle accelerators, have found no trace of it. Every attempt to catch this invisible cosmic scaffolding in action comes up empty. It exists because it must, and yet we have never directly seen it. Even stranger, as telescopes pushed further into the universe, another anomaly emerged. The early cosmos, we thought, should have been a chaotic place. Galaxies should have been small, irregular, and primitive, slowly merging over billions of years to form the spirals and ellipticals we see today. That was the expectation. But the James Webb Space Telescope, peering further back than any instrument in history, revealed galaxies that are far more massive and mature than theory allows. Some form stars at astonishing rates mere hundreds of millions of years after the Big Bang. Others already show well-defined spiral arms, organized structures that, according to simulations, should have taken billions of years to evolve. These findings do more than challenge timelines. They suggest that the rules of galaxy formation may be fundamentally misunderstood. The implications ripple outward. If massive galaxies existed so early, the universe itself must have evolved faster than our models predict. The interplay of dark matter, gas and energy that supposedly governs cosmic structure formation may be more complex, or perhaps completely different from what we assumed. The cosmos is no longer a slow, predictable clockwork. It is a stage where reality consistently outpaces expectation, and every observation forces theorists to rewrite the story. And then there is the oldest light in the universe, the cosmic microwave background, a relic from the time the universe became transparent, about 380,000 years after the Big Bang. For decades, it was considered the most precise confirmation of the Standard Model. The tiny fluctuations in the CMB encode information about the density, composition, and geometry of the early universe. But when scientists examined it in fine detail, they noticed patterns that should not exist. There are regions colder than theory predicts, patches where the statistical uniformity breaks down. One anomaly, famously dubbed the cold spot, is so large and so improbable that it cannot easily be dismissed as chance. Elsewhere, subtle asymmetries suggest the universe might have a preferred direction, a shocking revelation that challenges the assumption of isotropy. Each of these anomalies, rotation curves, unexpectedly mature galaxies, and irregularities in the CMB, paints a picture of a universe more complicated than the Standard Model can account for. Individually, they are puzzling. Together, they form a pattern impossible to ignore. The universe is behaving as if it has hidden rules, forces, or histories that remain invisible to our current instruments and theories. Cosmologists are now confronted with a stark choice. Either something in the measurements is flawed, a subtle bias lurking undetected in decades of observational data, or the universe itself is fundamentally different from what lambda CDM predicts. The implications are staggering. It is a puzzle not of mere details, but of cosmic principle. Gravity, star formation, the behavior of matter over billions of years all might need to be reconsidered. And as new instruments continue to probe deeper and earlier in cosmic history, these cracks become harder to ignore, impossible to rationalize away with minor tweaks to the existing model. The universe, it seems, is sending us a message through these anomalies. The cosmos is more intricate than our equations suggest. It is a place where invisible matter dominates, where galaxies can mature at impossible speeds, and where the earliest light carries hidden irregularities that refuse to be ignored. Scientists are chasing every clue, measuring every angle, modeling every possible scenario, because in these anomalies may lie the key to the next revolution in our understanding of the cosmos. And perhaps most unsettling of all, each discovery only deepens the mystery. The further we look, the more the universe seems to mock our assumptions. Every telescope, every survey, every painstaking measurement confirms a truth that is as beautiful as it is confounding. The universe is not the predictable, orderly expanse we once thought it was. It is a living puzzle, one that is only now revealing cracks in the framework we long trusted. Cracks that hint at secrets even older and stranger than the Big Bang. Galaxy rotation curves that refuse to behave. The universe, on its grandest scales, is a place of motion. Galaxies spin, stars orbit, and cosmic structures drift along invisible currents. For most of the 20th century, astronomers believed they understood the mechanics of these motions. They assumed that galaxies, massive collections of stars, gas and dust, would rotate much like our own solar system. Faster near the centre, where most of the mass is concentrated, and slower at the edges, where stars are more distant from the gravitational pull of the core. It seemed simple, elegant, a predictable cosmic dance choreographed by Newtonian gravity. Then came Vera Rubin. A pioneering astronomer in an era when women were rarely acknowledged in physics, Rubin looked deeper into the night sky than most of her contemporaries. Using spectroscopy, a technique that allowed her to measure the velocity of stars moving toward or away from Earth, she began to chart the rotational speeds of spiral galaxies. What she discovered was staggering. Galaxies were spinning in a way that should have been impossible. Stars far from the galactic center, where visible matter thinned out, were moving just as fast as stars near the dense core. According to the laws of gravity, these outer stars should have been flung out into intergalactic space, escaping the galaxy entirely. Yet they remained, tracing perfect orbits around the galactic center, defying every prediction. Rubin's observations were not isolated anomalies. Across dozens of galaxies, the same pattern appeared. Rotation curves that refused to drop off at the edges. The stars were moving too fast. The galaxies were too orderly, spinning like cosmic merry-go-rounds powered by more than just the visible matter we could detect. Every measurement, every spectrum, reinforced the same troubling conclusion. There had to be something else, something invisible, holding these galaxies together. This invisible something became known as dark matter. It was a concept born not from imagination, but from necessity, a placeholder for the missing mass that gravity demanded. If the luminous stars and gas clouds were not enough to account for galactic stability, then there had to be an unseen component exerting gravitational influence. A halo of matter wrapping around every galaxy, massive yet undetectable by conventional means. Dark matter was not merely a theory, it was an inference drawn from the stubborn behavior of the cosmos itself. And yet, nearly half a century after Rubin's discoveries, dark matter remains elusive. Countless experiments have attempted to detect these particles directly, from deep underground laboratories shielded from cosmic rays to giant tanks of liquid xenon and sophisticated detectors scanning for the faintest signs of interaction. The particles, if they exist, are ghostly, slipping through ordinary matter without leaving a trace. We can see their influence on galaxies, clusters, and the cosmic web, but we have never touched them, never measured them in a lab, never held proof of their existence in our hands. The problem is as profound as it is simple. Gravity tells us the matter is there, but our instruments cannot see it. The universe is behaving according to rules that do not match what we can detect directly. A cosmic trick played across billions of light years. Rubin's curves, once dismissed as curiosities or errors, now form one of the most compelling pieces of evidence for dark matter. Yet they also remind us of the limits of human understanding. We have a map of effects, but not the substance behind them. The stars continue to orbit, the galaxies continue to spin, and the question remains, what is holding it all together when everything we can see is far too little to explain it? Galaxy rotation curves that refuse to behave. Even as Vera Rubin's groundbreaking work became widely accepted, dark matter remained a ghost. It was the invisible architect of galaxies, shaping the cosmic scaffolding, yet remaining entirely untouchable. The problem was not that we lacked evidence. The evidence was everywhere, but that all of it was indirect. We see the effects of dark matter in galactic rotation curves, in the motion of galaxy clusters, and in the subtle bending of light from distant objects known as gravitational lensing. Yet no experiment, no detector, no telescope has ever captured dark matter itself. It is a universe-sized puzzle wrapped in a cosmic paradox. We know it's there because everything else behaves as if it is, but it continues to evade every attempt at direct detection. For decades, particle physicists and cosmologists have pursued the most promising candidates. The leading theory posits that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would rarely interact with normal matter, passing through planets, stars, and people almost entirely unnoticed. Experiments designed to catch a single particle striking an atomic nucleus have been set up in deep underground laboratories, shielded from cosmic radiation that could obscure the faintest signals. Tanks of liquid xenon, liquid argon, and even supercooled germanium detectors have waited patiently, recording events with precision instruments sensitive enough to detect a collision smaller than a single atom. And yet, after decades, the silence has been deafening. The particles remain invisible, their existence inferred only by the gravitational pull they exert on stars and galaxies. Other candidates have been proposed: axions, ultralight particles that could fill space and influence electromagnetic fields, or sterile neutrinos, exotic versions of ghostly subatomic particles already known to exist. Each comes with a theory, a detector, and a hope that the cosmic puzzle will finally yield a tangible piece of matter. Yet every attempt so far has failed, leaving the universe more mysterious than ever. Even as we peer deeper into space, from the outskirts of the Milky Way to the most distant galaxy clusters, the rotation curves Rubin first studied continue to defy simple explanation, demanding the presence of mass that cannot be accounted for by anything we can see, touch, or measure directly. What makes this puzzle even more profound is the scale of the discrepancy. Consider the Milky Way. The stars near the center orbit at roughly the same speed as stars tens of thousands of light years from the core, despite the fact that visible matter drops off dramatically with distance. Gravity, as we understand it, should dictate a slowdown at the edges. The fact that it does not implies that the mass of the Milky Way is far greater than the sum of stars, gas, and dust. And it is not a small difference. Estimates suggest that more than 80% of the galaxy's mass is invisible, contained in an enormous, roughly spherical halo of dark matter extending well beyond the luminous disk. And this is not unique to the Milky Way. Every spiral galaxy measured exhibits the same anomaly. The universe is insisting on an answer, but it refuses to give it in forms we can measure directly. The mystery does not stop with individual galaxies. Galaxy clusters, the largest gravitationally bound structures in the universe, also display motion inconsistent with visible matter. In the 1930s, Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast to be held together by their luminous mass. Rubin's work, decades later, confirmed that this was not a local oddity, but a universal phenomenon. In every structure, from small galaxies to the largest clusters, the same invisible hand governs the motion, demanding an explanation that remains tantalizingly out of reach. The search for dark matter is not just a question of curiosity. It is central to understanding the universe itself. Without dark matter, our models of galaxy formation collapse. Simulations fail to produce the large-scale structure we observe. Without it, the cosmic web of filaments, voids, and galaxy clusters could not have formed as it did. Rubin's rotation curves were not just a peculiar anomaly in a handful of galaxies. They were the first visible threads of a cosmic tapestry dominated by unseen mass, a puzzle that stretches from the scale of a single star's orbit to the entire observable universe. Even with modern instruments, the direct detection of dark matter remains the holy grail of physics. Experiments deep underground continue to push sensitivity limits, and astronomers scour the sky for gravitational clues. Colliders like the Large Hadron Collider attempt to recreate conditions where dark matter might be produced, but so far all attempts return empty-handed. Some scientists have begun to wonder if we are looking in the wrong place, or perhaps thinking too narrowly about what dark matter could be. Could it be composed of something entirely unexpected? Could it interact via forces we have yet to discover? The universe, it seems, is always one step ahead, leaving us to infer its rules while withholding the pieces we most desire. Vera Rubin's discovery, once dismissed by some as a curiosity, now forms one of the cornerstones of modern cosmology. It is a testament to the power of careful observation and relentless curiosity. Yet it also stands as a warning. The universe can obey its own logic, its own invisible laws, in ways that defy human expectation. The rotation curves of galaxies, stubborn and precise, tell a story of a cosmos dominated by something we cannot see, a hidden framework that has governed cosmic evolution since the dawn of time. Every star orbiting in the outskirts of a galaxy is a silent witness to this invisible mass, a reminder that even in an era of precision measurement, the universe still holds secrets that challenge our most fundamental assumptions. The lingering problem is as stark as it is compelling. We know dark matter exists because the universe behaves as if it does, but we cannot detect it directly. It is gravity without substance, a cosmic shadow that shapes galaxies, clusters, and the entire web of the cosmos. Rubin's curves were the first proof that the universe refuses to be fully revealed on our terms, and despite decades of effort, the mystery only deepens. Every observation, every measurement, every experiment reaffirms the same truth. Galaxies spin too fast. The universe is heavier than it looks, and dark matter, that invisible force holding it all together, remains one of the greatest unsolved enigmas in modern science. The James Webb Shock Disk. For decades, astronomers had peered into the cosmos with ever more sophisticated instruments, pushing the boundaries of what we could see, yet always constrained by the limits of visible light. Telescopes like Hubble revealed galaxies, nebulae, and stars in exquisite detail, but the earliest epochs of the universe, the first few 100 million years after the Big Bang, remained shrouded in mystery. To truly glimpse the infancy of the cosmos, scientists needed a new kind of vision, one that could pierce through clouds of gas and dust, reach across billions of light years, and detect the faint glow of the very first galaxies forming after the universe emerged from darkness. That vision became reality with the James Webb Space Telescope, the most advanced space observatory ever built. Webb was designed to operate primarily in infrared light, a wavelength longer than the visible spectrum, capable of revealing the heat signatures of distant, ancient objects. Unlike visible light, infrared can travel across the vast expanses of space while escaping absorption and scattering by interstellar gas and dust. In practical terms, this allowed Webb to look back further in time than any telescope before it, capturing the feeble radiation emitted by the universe's first generations of stars and galaxies. Scientists expected that these early galaxies would be small, irregular, and chaotic, clumps of gas barely coalescing into stars, building the foundation of cosmic structures gradually over billions of years. They anticipated slow structural formation, a universe in its adolescence, messy and unpredictable, lacking the large, ordered shapes seen in more mature galaxies. The mission parameters were clear: to map the dawn of galaxies, charting their growth, their star formation rates, and their chemical composition. Webb's infrared instruments, designed with unprecedented sensitivity, would measure the light stretched and reddened by cosmic expansion, allowing astronomers to calculate distances and ages of the earliest cosmic objects. Every aspect of the telescope from its segmented gold-coated mirrors to its orbit far from Earth's heat and light, was optimized to detect signals so faint they had previously been invisible, to pull into focus a universe that had long remained only theoretical in its earliest moments. In preparation for launch, models and simulations guided expectations. The first galaxies were predicted to be dim and irregular, scattered in size and mass, forming stars slowly, with few heavy elements. The universe at this time was thought to be turbulent, chaotic, and incomplete, a cosmic nursery just beginning to assemble the scaffolding of structure. Any detection of well-formed galaxies at this stage would have been surprising, but the models left little room for fully mature, massive, or chemically enriched galaxies in the first billion years. Webb was expected to confirm this slow, gradual emergence of cosmic order, filling in the details that Hubble and other observatories could hint at, but never fully reveal. Webb's instruments were tuned to capture this narrative of cosmic youth. Its near-infrared camera, NIRCam, could detect the faintest starlight from early galaxies, while its mid-infrared instrument, MIRI, probed the dust-obscured star-forming regions that had remained invisible to previous missions. Its spectrographs allowed scientists to analyze the chemical composition of these nascent galaxies, measuring elements heavier than hydrogen and helium produced by the first generations of stars. This data promised to illuminate the process of early galaxy assembly, tracing how small clumps of gas merged, formed stars, and gradually grew into the structures we observe in the modern universe. Every calculation, every simulation reinforced the expectation that Webb would see the universe as it was predicted to be: small, primitive, slow to form, and chaotic. The models portrayed a gradual narrative, one of incremental growth, a universe assembling itself over billions of years, with the largest galaxies only appearing long after the first stars flickered to life. Webb's mission was to test these predictions, to provide a window into an epoch that had, until then, been accessible only through theory, limited Hubble imaging, and indirect inferences. The stage was set, instruments aligned, and the astronomical community braced for confirmation of decades of theoretical expectations, unaware that Webb was about to reveal something far more astonishing than anyone had imagined. What James Webb actually found. When the James Webb Space Telescope finally sent its first images back to Earth, astronomers around the world were prepared for confirmation, expecting glimpses of small primitive galaxies scattered across the early universe, irregular clumps of gas just beginning the slow process of star formation. What Webb revealed, however, was a universe far stranger and far more advanced than anyone had dared imagine. Instead of scattered cosmic toddlers, Webb unveiled galaxies that were already massive and mature, forming stars at rates and in numbers that challenged the most sophisticated models of cosmic evolution. These early galaxies, existing less than 1 billion years after the Big Bang, were not the chaotic, disorganized systems scientists had predicted. Many exhibited well-defined spiral structures, elegant disks of stars sweeping outward from a central bulge, reminiscent of galaxies like the Milky Way, which should have required billions of years to form. Webb's infrared vision, capable of penetrating vast cosmic distances and the obscuring clouds of dust, revealed spiral arms fully in place, with star-forming regions clearly delineated along their curves. The symmetry and organization of these galaxies were staggering, suggesting that the forces shaping cosmic structures were operating far faster and more efficiently than existing theory allowed. Equally astonishing was the stellar mass contained within these young galaxies. Observations indicated that some of these systems contained billions of stars, rivaling or exceeding the size of present-day galaxies. Yet they existed at a cosmic epoch when the universe was expected to be dominated by small, scattered objects still in the process of assembling. This implied an incredibly rapid accumulation of mass, a level of galactic construction that standard models simply could not account for. Stars were forming at extraordinary rates, condensing gas into stellar furnaces far more quickly than anticipated. These were not fledgling systems, they were mature, complex, and already dominating their local cosmic neighbourhoods. Webb's spectroscopic instruments added yet another layer of mystery. By analysing the light from these early galaxies, astronomers could measure their chemical composition, looking for the presence of elements heavier than hydrogen and helium. These metals, as astronomers call them, are forged in the cores of stars and spread through supernovae. Surprisingly, Webb detected significant chemical maturity in galaxies from the universe's first billion years. Instead of being dominated by pristine hydrogen and helium, these galaxies contained higher abundances of heavier elements, indicating that multiple generations of star formation had already occurred. The early universe, it seemed, had been far more efficient at creating stars and recycling their elements than any theory had predicted. The combination of size, structure, and chemical enrichment was more than unexpected. It was revolutionary. These galaxies were massive, with dense stellar populations, ordered spiral arms, and complex chemical signatures, the hallmarks of mature galactic systems. They existed in a time when conventional models predicted only small, disordered galaxies gradually building up over billions of years. Webb's data forced astronomers to confront a reality in which galaxy formation was accelerating faster and more efficiently than the standard model of cosmology could explain, raising profound questions about the physics driving the early universe. Even the most advanced cosmological simulations struggled to reproduce what Webb had observed. Models designed to predict the evolution of structure in the first billion years failed to produce spiral arms so early, or stellar masses so high, or chemical abundances so advanced. The sheer scale and organisation of these galaxies suggested that the processes of star formation, gas accretion, and galactic stabilisation were operating at efficiencies far beyond anything previously considered possible. The early universe was not a simple, chaotic nursery of stars. It was a bustling metropolis of galaxies, already large, structured, and chemically sophisticated. Webb's findings also hinted at the possibility that cosmic evolution may follow pathways far more varied and complex than previously imagined. The presence of mature spiral galaxies at such early times suggests that the mechanisms driving galactic growth, from gas inflows to starburst episodes to the merging of smaller proto-galaxies, can operate on timescales far shorter than expected. These galaxies were not anomalies or rare exceptions. Multiple massive systems have been observed across Webb's initial surveys, indicating that this rapid maturation may have been a common feature of the early cosmos. The universe, as Webb revealed it, was already structured, organised, and chemically rich within the first billion years, defying the predictions of decades of theory. Where scientists expected small, chaotic galaxies, they found spiralling giants. Where theory anticipated slow growth, Webb revealed rapid assembly. Where models predicted primitive chemistry, Webb detected advanced stellar processing. Every image, every spectrum, every data point seemed to whisper the same message. The universe is far more efficient, far more mature, and far more sophisticated in its earlier stages than we ever imagined. James Webb did not simply confirm expectations, it shattered them, revealing a universe that had already grown up while we were still learning to read its story. Its findings forced astronomers to reconsider the timeline of galaxy formation, the physics of early star formation, and the processes that allow complex structures to emerge from the primordial chaos of the Big Bang. The cosmic microwave background anomalies. Long before galaxies spun into majestic spirals, before stars filled the universe with light, before planets formed and cosmic structures stretched across billions of light years, there was a faint glow left over from the very beginning, the cosmic microwave background, or CMB. It is the oldest light in the universe, a whisper of the cosmos' first moments, emitted when the universe was just 380,000 years old, still a hot plasma of charged particles. At that time, the universe had cooled enough for protons and electrons to combine into neutral atoms, allowing photons, particles of light, to travel freely for the first time. Those photons have been moving through space ever since, stretched and cooled by the expansion of the universe, now detectable as microwave radiation bathing every corner of the sky. The CMB is often called the universe's birth record because it preserves the earliest imprint of cosmic conditions. Its faint temperature variations, uneven by just 1 part in 100,000, contain the seeds of all structure, the tiny density fluctuations that would eventually grow into galaxies, clusters, and the vast filaments spanning the cosmos. It is a snapshot of the universe in its infancy, capturing the balance between gravity and pressure, the primordial energy fluctuations, and the blueprint for everything that would follow. By studying the CMB, astronomers can trace the composition of the early universe, measure the amount of ordinary matter and dark matter, and even calculate the universe's age and geometry with remarkable precision. What makes the CMB extraordinary is that it is a direct window into the past, unlike galaxies or stars, which formed hundreds of millions or billions of years later. It is light that has travelled almost the entire history of the universe, carrying information untouched by cosmic events, preserved across time. Instruments like the COBE, WMAP and Planck satellites have mapped its minute fluctuations with incredible accuracy, revealing a nearly uniform universe, but with subtle irregularities that provide critical clues about the early cosmos. Each temperature variation in the CMB corresponds to a tiny over or underdensity in the primordial plasma, a region where matter would eventually clump or disperse, shaping the large-scale structure of the universe. For decades, these measurements confirmed the standard cosmological model, a universe born from the Big Bang, expanding ever since, dominated by dark matter and dark energy. The CMB appeared smooth, almost featureless, with fluctuations that matched theoretical predictions. It seemed like the universe was following the script scientists had written, and the birth record confirmed their expectations. Yet as instruments grew more precise and maps became more detailed, anomalies began to appear. Tiny irregularities, patterns in the temperature variations that should have been random, began to suggest that the universe might not be quite as simple as the standard picture implied. Certain large-scale temperature differences, alignments, and cold spots appeared across the sky, patterns that did not fit neatly with predictions. Even the most subtle features mattered. The CMB is not just a uniform glow, it contains the detailed fingerprint of the universe's earliest moments. The anomalies, small as they are, hint that something unexpected occurred during the first fraction of a second, during inflation or in processes that set the initial conditions for cosmic evolution. These irregularities, while minute, are persistent across multiple datasets and instruments, suggesting that they are not random errors, but intrinsic features of the oldest light in the universe. The universe, it seems, encoded hints of a story that is not fully understood, whispers of physics beyond what current models can explain. The unexpected patterns in the cosmic microwave background. The cosmic microwave background is a relic radiation from the early universe, a snapshot of the cosmos approximately 380,000 years after the Big Bang. While it is remarkably uniform at roughly 2.725 kelvins, precise measurements, particularly from the WMAP and Planck satellites, reveal subtle temperature fluctuations on the order of microkelvins. These fluctuations encode the seeds of cosmic structure, the early density variations that eventually formed galaxies, clusters, and voids. However, Beyond the expected random variations predicted by the standard lambda CDM cosmological model, several unexpected patterns have emerged, challenging assumptions about the universe's large-scale isotropy. One of the most striking discoveries in the CMB is the presence of large-scale temperature asymmetries. These asymmetries manifest as a subtle but statistically significant difference in the amplitude of temperature fluctuations across opposite hemispheres of the sky. In practice, when the CMB is divided into two hemispheres along certain axes, one side appears slightly hotter and the other slightly cooler than the average expected from a purely random isotropic distribution. Researchers quantify this by measuring the power spectrum of temperature fluctuations at low multipoles, which correspond to angular scales greater than approximately 60 degrees. At these large scales, the fluctuation should, in theory, be uniform in all directions. Yet the observed variance is uneven, with some hemispheres showing consistently stronger or weaker fluctuations. This asymmetry persists across independent datasets, including WMAP and Planck, suggesting it is not merely an artifact of measurement or foreground contamination. The origin of this asymmetry remains an open question, as it may indicate a violation of statistical isotropy on cosmological scales. Detailed analyses involve rotating the coordinate system and evaluating the variance along multiple axes, revealing a preferential orientation in the fluctuation patterns. This alignment hints at an underlying structure or process in the early universe that imprinted directional features onto the CMB. Closely related to the hemispherical asymmetry is a phenomenon dubbed the axis of evil. This term describes a curious alignment of the low multipole moments, specifically the quadrupole and octopole components of the CMB temperature fluctuations along a common axis in space. In standard cosmology, the quadrupole L equals 2 and octopole L equals 3 should be randomly oriented. Instead, their spatial alignment suggests a preferred direction that extends across the observable universe. The axis of evil is measured by decomposing the CMB temperature map into spherical harmonics and examining the angular momentum dispersion of the quadrupole and octopole moments. Analysis shows that these multipoles are not only unusually planar, but also point toward a common direction approximately along the ecliptic plane of the solar system. While initial skepticism proposed that this alignment could result from residual contamination by foreground emissions or observational biases, subsequent studies with Planck data confirmed the persistence of the alignment, even after careful subtraction of galactic and extragalactic sources. The alignment raises significant questions because the cosmological principle, a foundation of modern cosmology, assumes that the universe is isotropic and homogeneous at large scales. A preferred axis challenges this assumption and implies the existence of large-scale structures or early universe physics that introduce directional asymmetry, possibly linked to anomalies in inflationary processes or other unknown mechanisms. Another feature that deviates from the expected Gaussian fluctuations is the cold spot, an unusually large region in the CMB that appears significantly colder than its surroundings. Located in the southern hemisphere of the sky, the cold spot spans approximately 10 degrees in angular size and exhibits a temperature decrement of roughly -150 microkelvins relative to the CMB mean. The cold spot is identified using wavelet and statistical analyses, which enhance its contrast against the background fluctuations. Its scale and depth are inconsistent with typical random fluctuations predicted by the standard cosmological model, where temperature deviations follow a nearly Gaussian distribution. While smaller cold and hot regions are expected throughout the sky, the cold spot's size and statistical significance stand out as exceptional, placing it in the tail of the probability distribution. Several hypotheses have been proposed to explain the cold spot. One class involves line-of-sight effects, such as the integrated Sachs-Wolf effect, where photons traversing large-scale voids lose energy, producing apparent temperature decrements in the observed CMB. Another approach considers the possibility of primordial non-Gaussianity, where the cold spot could be a relic of early universe processes that generated unusually large perturbations. Despite extensive studies, the anomaly's origin remains uncertain, and it continues to be a focal point for both observational and theoretical cosmology. Interestingly, these unexpected features, large-scale asymmetries, the axis of evil, and the cold spot, are not entirely independent. Statistical analyses suggest potential correlations, where the regions associated with low multipole alignments may overlap with areas containing temperature extremes. The combination of planar multipoles, hemispherical power asymmetry, and isolated cold regions indicates that the CMB exhibits patterns that are highly structured at the larger scales, challenging the notion that primordial fluctuations are purely random. Researchers apply sophisticated statistical techniques, such as Monte Carlo simulations and null tests, to quantify the likelihood of these coincidences under standard cosmological assumptions. While each anomaly individually could occur with low but non-zero probability, their simultaneous presence intensifies scrutiny. Large-scale temperature patterns are evaluated with masking procedures to account for galactic foregrounds, ensuring that these anomalies are intrinsic to the cosmic signal rather than observational artifacts. Why these patterns should not exist. Some of the most striking discoveries in modern cosmology come from looking at the oldest light in the universe, the cosmic microwave background. This faint glow, a remnant of the universe just 380,000 years after the Big Bang, should be remarkably uniform. Tiny fluctuations exist, but at the larger scales, those fluctuations are expected to be random, the same in every direction. Instead, scientists have found patterns that simply should not exist. These patterns begin with temperature differences across the sky that are far larger than expected. When researchers examine the CMB, one side of the universe appears slightly hotter, while the opposite side is cooler. The difference is subtle, measured in millionths of a degree, yet persistent. Every dataset, from WMAP to Planck, confirms it. The universe appears to have a preferred direction, a slight tilt, in what should be complete isotropy. It is as if the cosmos itself is subtly lopsided. Even more puzzling is what scientists have called the axis of evil. At the largest angular scales, certain temperature fluctuations align along a common axis. The quadrupole and octupole moments, which should be randomly oriented, instead point toward a particular region of the sky, almost coinciding with the plane of our solar system. This alignment is extraordinary because standard cosmology assumes there is no cosmic north or south, no preferred orientation. Yet here it is, encoded in the fabric of the early universe, stubbornly resisting explanation. The cold spot adds another layer of mystery. A vast, unusually chilly region stretches across 10 degrees of the sky, far larger and colder than predicted by the standard models. It is not just a small deviation, it is an anomaly that statistical analyses have repeatedly confirmed. Some theories suggest it could be caused by enormous cosmic voids along our line of sight, but the effect is too extreme to be easily explained. It hints at processes in the early universe that were far from uniform. Together, these features challenge our deepest assumptions about the cosmos. If the universe were truly isotropic, none of these patterns should be detectable. The large-scale temperature asymmetries, the axis of evil, and the cold spot all point to a universe that appears slightly directional, a cosmos that may have preferred orientations etched into its earliest moments. For inflation theory, which predicts a uniform stretching of space that smooths out any irregularities, these patterns are particularly confounding. The anomalies suggest that either inflation was not as simple as current models describe, or that additional mechanisms operated during those first fractions of a second. Astronomers continue to probe these irregularities, mapping them with incredible precision, searching for correlations and clues hidden in the microwave sky. Every survey, every map, seems to reinforce the idea that the universe is not as perfectly random as once assumed. The sky carries memory, hints of processes that shape the cosmos on scales so vast they almost defy comprehension. What dark energy was supposed to be. When astronomers first realized the universe was not just expanding, but accelerating, the discovery stunned the scientific community. Galaxies were not merely drifting apart from one another as a leftover consequence of the Big Bang. They were speeding away faster and faster over time. Something unseen was overpowering gravity on the largest scales imaginable. To explain this unexpected behavior, scientists introduced a new component into the cosmic framework: dark energy. Dark energy was not observed directly. It did not emit light, absorb radiation, or interact with matter in any measurable way. Instead, its presence was inferred through motion, specifically the motion of galaxies across billions of light-years. Type 1. A supernovae, used as precise cosmic distance markers, appeared dimmer than expected. The simplest explanation was that space itself was stretching at an accelerating rate. To make sense of this, dark energy was defined as a constant force embedded in space, acting everywhere, at all times, with unwavering strength. In this picture, dark energy behaved like an intrinsic property of the universe. It did not clump or dilute as space expanded. Unlike matter, which thins out as the universe grows larger, dark energy's density remained fixed. As the universe expanded, there was simply more space for dark energy to exist within, allowing its influence to grow stronger over time. This assumption made dark energy mathematically clean and observationally convenient. It fit neatly into Einstein's equations as the cosmological constant, represented by the Greek letter lambda, lambda. Under this model, dark energy exerted a uniform pressure across the cosmos. Its effect was identical in all directions and at all locations. No region of space experienced more or less of it. This uniformity ensured that the universe expanded smoothly on large scales, without distortions or directional bias. The acceleration of cosmic expansion followed a predictable curve, one that could be calculated precisely using redshift measurements and distance data from distant galaxies. This assumption of uniform acceleration became foundational. As space expanded, galaxies moved apart faster with increasing distance, not because they were traveling through space at high speed, but because space itself was stretching between them. Dark energy did not push galaxies outward like an explosion. It caused the fabric of the universe to swell. The farther apart two galaxies were, the more space existed between them, and the more dark energy acted within that space, leading to stronger acceleration. The idea of dark energy as a constant force explained why cosmic acceleration appeared smooth and steady when observed across vast distances. Measurements taken at different epochs of cosmic history seem consistent with the universe transitioning from matter-dominated expansion to dark energy-dominated acceleration. Once dark energy took over, the expansion rate no longer slowed under gravity's influence. Instead, it steadily increased. This framework allowed cosmologists to build predictive models. The future of the universe could be calculated under the assumption that dark energy would never weaken, fluctuate, or change its behavior. Galaxies outside local gravitational groups would continue to drift beyond observable reach. Cosmic structures would become increasingly isolated. The large-scale geometry of the universe would remain flat, balanced delicately between collapse and runaway expansion. The assumption of constancy also simplified the early universe. Dark energy played no significant role in galaxy formation or early cosmic structure, because its influence only became dominant billions of years after the Big Bang. This separation of eras, gravity shaping structure early on, dark energy taking over later, made the model internally consistent and computationally stable. For decades, observations reinforced this view. Data from supernova surveys, galaxy clustering, and the cosmic microwave background all aligned closely enough with a constant dark energy model to make it the default explanation. The cosmological constant became one of the most important terms in modern physics, despite its mysterious origin and lack of direct detection. Dark energy, as it was supposed to be, required no complexity. It did not evolve, it did not vary, it did not interact, it simply existed, silently accelerating the universe at a steady, uniform rate, shaping cosmic expansion without ever revealing its true nature. The observations that changed everything. The idea of dark energy as a perfectly steady, unchanging force did not collapse overnight. It began to erode quietly, not through theory, but through observations, measurements so precise that small inconsistencies could no longer be ignored. The same tools that once supported the picture of uniform acceleration started revealing cracks in it. The first pressure came from supernova surveys, the very method that originally led to the discovery of cosmic acceleration. Type 1a supernova are used as cosmic distance markers because they explode with nearly identical brightness. By comparing how bright they appear from Earth to how bright they are known to be, astronomers can calculate their distance. When those distances are matched with redshift measurements, the expansion history of the universe can be reconstructed. As supernova surveys expanded in scale and depth, covering larger volumes of space and longer stretches of cosmic time, subtle discrepancies emerged. Supernovae at different redshifts did not all align perfectly with predictions made by a constant dark energy model. Some appeared slightly brighter or dimmer than expected, depending on how far back in time they were observed. These deviations were small, but they appeared consistently across independent datasets. Teams running surveys like the Supernova Legacy Survey and the Dark Energy Survey began to notice that the acceleration rate inferred from distant supernovae did not always match the acceleration rate inferred from nearer ones. The universe's expansion history, when reconstructed in detail, showed hints of variation, as if the influence driving acceleration had not remained identical across billions of years. At first, these irregularities were treated cautiously. Astronomers scrutinized calibration methods, dust effects, selection biases, and instrumental uncertainties. Supernova measurements are notoriously delicate, and no one was eager to rewrite cosmology based on marginal signals. Yet as datasets grew larger and methods improved, the patterns refused to disappear. A more powerful challenge arrived with the early results from DESI, the Dark Energy Spectroscopic Instrument. DESI was designed to map the three-dimensional structure of the universe with unprecedented precision by measuring the spectra of tens of millions of galaxies and quasars. Its primary goal was to track how cosmic expansion evolved over time by observing how galaxies are distributed across vast distances. DESI does not rely on brightness alone. It measures redshifts directly and maps large-scale structures such as baryon acoustic oscillations, subtle ripples in the distribution of galaxies left over from the early universe. These ripples act as a cosmic ruler, allowing astronomers to measure how space has expanded at different epochs. When DESI's early data were analysed, something unexpected emerged. The expansion history inferred from galaxy clustering and large-scale structure did not line up perfectly with the predictions of a constant dark energy model. The rate at which expansion appeared to accelerate at certain cosmic times showed tension with earlier measurements derived from the cosmic microwave background and supernova data. Rather than a smooth, single-curve acceleration, the data hinted at shifts, slight changes in how strongly dark energy influenced expansion at different periods in cosmic history. The effect was not dramatic enough to be obvious in any single measurement, but when combined across multiple probes, a pattern began to form. These findings suggested that dark energy might not behave like a fixed background property of space. Instead, its strength could be changing gradually, evolving as the universe expands. This possibility fundamentally alters how cosmic expansion is interpreted. If dark energy evolves, then the assumptions built into decades of cosmological modeling no longer hold. The evidence did not point to randomness. Independent observational methods, supernova distances, galaxy clustering, and large-scale structure measurements were all indicating small but consistent deviations from the constant model. These signals appeared across different instruments, observing strategies, and analysis techniques, reducing the likelihood that they were artifacts of measurement error. What made this especially disruptive was that the deviations were time-dependent. The farther back astronomers looked, the more the expansion history appeared to drift from expectations. This behavior is difficult to reconcile with a cosmological constant, which by definition cannot change. A constant force cannot produce evolving effects without violating its own assumptions. As more DESI data were collected and cross-checked with other surveys, the possibility that dark energy evolves over time became increasingly difficult to dismiss. The universe's acceleration no longer looked like a simple, steady process. Instead, it appeared dynamic, with a history that may be more complex than a single number plugged into an equation. The observations did not identify what dark energy is, but they did something equally significant. They challenged the idea that its behavior is fixed. The expansion of the universe, once thought to follow a clean and predictable trajectory, began to resemble a process shaped by something that changes with time, quietly altering the cosmic balance as the universe ages. Einstein's cosmological constant. For decades, modern cosmology rested on a fragile but elegant assumption that the force accelerating the universe was simple, steady, and unchanging. Once observations began to suggest otherwise, the consequences were immediate and far-reaching. The moment dark energy showed signs of evolution, some of the most trusted pillars of cosmology began to wobble, not gradually, but all at once. At the center of this disruption sits Einstein's cosmological constant. When Einstein first introduced the cosmological constant into his equations of general relativity, it was meant to counteract gravity and hold the universe static. After the discovery that the universe was expanding, Einstein famously abandoned it. Decades later, it returned in a new role, reinterpreted as dark energy, a constant energy density of empty space itself. In this form, the cosmological constant was mathematically clean, observationally useful, and incredibly convenient. The key word was constant. Lambda, by definition, does not change with time. Its energy density remains fixed even as space expands. This property made it uniquely powerful. It allowed cosmologists to describe cosmic acceleration using a single number. No evolution, no dynamics, no internal structure. Just a smooth, uniform influence stretching space everywhere equally. Once observations hinted that dark energy might be evolving, this interpretation began to fracture. A changing acceleration rate cannot be produced by a true cosmological constant without breaking the mathematics that define it. If lambda varies, then it is no longer lambda. The term loses its physical meaning, and Einstein's elegant solution collapses into contradiction. This does not merely tweak general relativity, it challenges how vacuum energy is treated within the theory. The cosmological constant links quantum fields, space-time geometry, and cosmic expansion into a single framework. Altering its behavior forces physicists to confront unresolved tensions between quantum mechanics and gravity that had been temporarily buried under lambda's simplicity. The damage does not stop there. The lambda CDM model, the standard model of cosmology, is built around the cosmological constant as one of its core components. Lambda CDM combines cold dark matter with dark energy in the form of lambda, producing a universe that expands, forms structure, and evolves in a way that closely matches many observations. Its success lies in balance. Dark matter pulls matter together. Dark energy pushes space apart. Lambda acts as the stabilizing term that keeps this balance predictable. If dark energy evolves, lambda CDM loses that stability. The equations governing structure formation depend critically on how dark energy behaves over time. A constant lambda ensures that galaxies form early, clusters grow at a known rate, and large-scale structure freezes out in a predictable way. If dark energy changes strength, even slightly, the growth history of cosmic structures shifts. Galaxy clusters could form earlier or later than expected. Filaments could grow differently. Voids could expand at altered rates. This creates cascading inconsistencies. Simulations that once matched observations now require adjustments. Parameters that were previously fixed become time-dependent. The model grows more complex, less predictive, and harder to constrain. What was once a tight framework starts to resemble a patchwork of corrections. Lambda CDM's power came from its restraint. It explained the universe with remarkably few ingredients. Once lambda loses its constancy, that restraint disappears. New fields, new dynamics, or new forms of energy must be introduced to replace it. Each addition increases uncertainty and weakens the model's claim to completeness. The most unsettling consequence emerges when looking forward instead of backward. The long-term predictions of cosmic fate rely entirely on dark energy's behavior. Under a constant lambda, the universe expands forever. Galaxies drift beyond observable reach. Star formation fades, and the cosmos cools into a quiet, isolated future. This scenario is not speculation. It is a direct mathematical outcome of lambda's unchanging pressure. An evolving dark energy erases that certainty. If dark energy weakens over time, cosmic acceleration could slow, allowing gravity to regain influence on large scales. Structures thought to be drifting apart forever might stabilize. Expansion might approach a steady state rather than accelerating endlessly. If dark energy strengthens, the opposite occurs. Expansion accelerates more violently, stretching space faster and faster. Galaxies, star systems, and eventually atomic structures could be torn apart as space overwhelms all binding forces. The timeline and severity of such an outcome depend entirely on how dark energy evolves. If dark energy oscillates or changes direction, entirely new futures emerge, none of which fit neatly into existing models. These outcomes are not philosophical possibilities. They are direct consequences of equations sensitive to dark energy's behavior. A small change early on compounds over billions of years, reshaping the destiny of the universe itself. What once felt settled now feels exposed. Einstein's cosmological constant, long treated as a quiet background feature, becomes a point of failure. Lambda CDM, once praised for its elegance and accuracy, becomes vulnerable to observational pressure. The future of the universe, once charted with confidence, becomes uncertain again, not because of speculation, but because the data no longer agrees with the assumptions that held everything together. Cosmic Webb expectations. When cosmologists model the universe on its largest scales, they begin with a simple assumption. Beyond a certain distance, the universe should look the same everywhere. Not just similar, but statistically indistinguishable. This idea, known as large-scale uniformity, sits at the core of modern cosmology. It does not describe individual galaxies or clusters, but the overall distribution of matter across hundreds of millions and billions of light years. Under this assumption, matter in the universe should spread out in a way that appears random over vast distances. Local structures are expected. Galaxies group together, clusters form, superclusters emerge. But once those structures are averaged over large enough scales, any preferred patterns should disappear. The universe, when viewed from far enough away, should resemble a smooth cosmic fog, with no direction, no alignment, and no repeating structures. This expectation comes directly from the physics of the early universe. Shortly after the Big Bang, matter was distributed almost uniformly, with only tiny fluctuations in density. These fluctuations, seen in the cosmic microwave background, were extremely small. Gravity then amplified them over time, pulling matter together into denser regions. However, gravity operates locally. Its influence weakens with distance. It cannot coordinate structure across billions of light years without violating known physical limits. As a result, cosmological simulations predict that while matter should form a web-like pattern on moderate scales, filaments connecting clusters surrounded by voids, this structure should fade into randomness when examined across larger volumes. Filaments should not line up across enormous distances. Voids should not show coordinated shapes. Any apparent patterns should dissolve once enough space is considered. This leads to the expectation of statistical uniformity. In practice, this means that if astronomers measure galaxy density, clustering strength, or alignment in one direction, the same measurements should hold in any other direction, provided the sample size is large enough. The universe should have no large-scale preferences. No cosmic direction should look different from another. No region should appear more organized than the rest once averaged properly. This principle underpins how distances are measured, how expansion is calculated, and how cosmological parameters are inferred. It allows astronomers to treat the universe as a single system rather than a collection of disconnected regions. Without statistical uniformity, the equations describing cosmic expansion become unstable, and comparisons between distant regions lose meaning. Surveys like the Sloan Digital Sky Survey were designed with these expectations in mind. By mapping millions of galaxies across enormous volumes of space, astronomers expected to see clustering on smaller scales and smoothness on larger ones. The cosmic web was not supposed to extend endlessly. Its filaments were expected to break down, overlap, and cancel out into randomness. The reasoning behind this expectation is deeply rooted in probability. The early universe's density fluctuations were random, Gaussian in nature, and uncorrelated beyond small distances. When such fluctuations grow under gravity, they create structure, but they do not generate long-range coordination. Large-scale patterns require communication across vast distances, and nothing in standard cosmology provides a mechanism for that kind of coordination after inflation ends. In other words, the cosmic web was expected to be locally structured, but globally bland. Galaxies would trace filaments, clusters would sit at intersections, voids would open up between them, but step back far enough, and the pattern should blur into uniformity. The universe should not display coherent structure on scales so large that gravity, time, and causality cannot reasonably account for their formation. These expectations were not casual guesses. They were built into decades of theoretical work, numerical simulations, and observational planning. They shaped how astronomers interpreted surveys, filtered data, and defined cosmic averages. The assumption of randomness and uniformity at large scales was not optional. It was foundational. According to these expectations, the universe should have limits to its organization. Beyond those limits, structure should dissolve into statistical noise. The cosmic web should have an edge, not a continuation. Anything beyond that edge was expected to look the same no matter where or how it was measured. That was the universe cosmologists expected to find when they mapped the sky in detail. A cosmos rich in structure up close, but fundamentally smooth, random, and uniform when viewed across the largest distances imaginable. The Sloan Great Wall. When astronomers began mapping the universe with surveys deep enough to test large-scale predictions, they expected confirmation of limits. The cosmic web was supposed to thin out, blur, and lose coherence beyond a certain scale. Instead, the maps revealed something far more unsettling. Structures so large that they should not exist at all, at least not under the rules cosmology was built on. These were not minor deviations or statistical curiosities. They were enormous, coherent structures spanning billions of light years, dwarfing anything predicted by simulations. Their sheer size alone placed them beyond the theoretical ceiling for cosmic organization. They were not isolated clusters or filaments. They were vast, connected regions of matter stretching across volumes of space that should have been statistically uniform. Two discoveries in particular forced cosmologists to confront this contradiction directly: the Sloan Great Wall and the Hercules Corona Borealis Great Wall. The Sloan Digital Sky Survey was designed to test cosmology at scale. It mapped the positions and redshifts of millions of galaxies, creating a three-dimensional picture of the universe extending hundreds of millions of light years in every direction. The goal was not to hunt for anomalies, but to confirm that structure faded into uniformity when averaged over large volumes. What the survey uncovered instead was a structure so massive it immediately raised alarms. The Sloan Great Wall is a colossal assembly of galaxy clusters and filaments extending roughly 1.37 billion light-years in length. It is not a single object, but a connected system of dense regions linked by filaments, forming a massive wall-like structure in space. At the time of its discovery, it was the largest known structure in the universe. This alone was a problem. According to standard cosmological models, the universe should not contain coherent structures larger than roughly 1.2 billion light-years. Beyond this scale, matter distribution is expected to smooth out due to the random nature of early density fluctuations and the limits imposed by cosmic expansion and causality. The Sloan Great Wall exceeded that threshold. It was not only its length that troubled scientists, but its coherence. The galaxies within this structure were not randomly scattered. They showed clear clustering and connectivity across the entire span. This implied coordination in matter distribution across distances where no known physical mechanism could enforce such organization after the early universe. Simulations based on lambda CDM struggled to reproduce anything comparable. While rare large structures could emerge in simulations by chance, structures of this size and density were statistically improbable. The Sloan Great Wall was not supposed to appear in a universe governed by random initial conditions, amplified only by gravity. Attempts were made to classify it as a statistical fluke, a rare alignment exaggerated by the way the data was sliced. Yet follow-up analyses confirmed its reality. Independent measurements, alternative clustering algorithms, and different thresholds all pointed to the same conclusion. The structure was real, massive, and coherent. Even then, some cosmologists argued that while unsettling, the Sloan Great Wall might still fit within the extreme tail of probability. The universe is vast, and rare events can occur. That argument held briefly. Then something far larger appeared. The Hercules Corona Borealis Great Wall. The discovery of the Hercules Corona Borealis Great Wall changed the conversation entirely. Unlike the Sloan Great Wall, this structure was not identified through galaxy surveys alone. It was detected through the distribution of gamma-ray bursts, the most energetic explosions in the universe. These bursts occur when massive stars collapse or neutron stars merge, making them visible across enormous cosmic distances. Because gamma-ray bursts can be observed from the early universe, they provide a way to trace matter distribution far beyond the reach of conventional galaxy surveys. When astronomers plotted the positions of gamma-ray bursts across the sky, they noticed something impossible to ignore: a massive clustering in a specific region corresponding to the constellations Hercules and Corona Borealis. This was not a small overdensity. The Hercules Corona Borealis Great Wall spans an estimated 10 billion light-years, making it the largest known structure in the observable universe. To put that into perspective, the observable universe itself is about 93 billion light-years across. This single structure occupies a significant fraction of cosmic volume. Its size exceeds theoretical limits by orders of magnitude. There is no ambiguity here. No standard cosmological model allows for a structure this large, not even at the extreme edges of probability. The scale of the Hercules Corona Borealis Great Wall goes far beyond what random density fluctuations could produce, even when amplified over billions of years. The structure appears as a massive region where gamma-ray bursts are far more frequent than expected, indicating a corresponding overdensity of matter. This suggests an underlying concentration of galaxies, clusters, and large-scale structures extending across distances that should be causally disconnected. This creates a direct conflict with the assumption of statistical uniformity. If the universe is uniform on large scales, no region should dominate such a vast volume. Overdensities should cancel out when averaged across enough space. Yet here was a structure so large that it could not be averaged away without redefining what large scale even means. Attempts to explain it away as observational bias or selection effects were explored extensively. Gamma-ray burst detection is complex, influenced by instrumental sensitivity and sky coverage. However, even after accounting for these factors, the clustering remains statistically significant. The structure was not an illusion. Why these structures exceed size constraints? The problem is not merely that these structures are big. The problem is why they exist at all. Cosmological size constraints are not arbitrary. They emerge from well-defined physical principles. The early universe contained tiny density fluctuations, nearly uniform across space. Inflation stretched these fluctuations to cosmic scales, but it also smoothed them out. After inflation ended, no mechanism existed to coordinate matter across enormous distances. Gravity builds structure slowly. It pulls matter together locally, forming stars, galaxies, clusters, and filaments. Its influence weakens with distance and time. It cannot organize matter coherently across billions of light years unless those regions were already correlated from the beginning. That correlation is not present in standard models. The maximum expected scale of structure is determined by the size of the largest density fluctuations imprinted in the early universe and by how much time gravity has had to amplify them. Both place strict upper limits on coherence. The Sloan Great Wall already presses against those limits. The Hercules Corona Borealis Great Wall obliterates them. These structures imply one of several unsettling possibilities. The early universe contained larger scale correlations than currently modelled. Inflation behaved differently than assumed. Matter distribution was not as random as expected, and large-scale homogeneity breaks down at scales once thought safe. None of these options fit comfortably within lambda CDM. Simulations attempting to reproduce these structures require either extreme initial conditions or modifications to dark matter behaviour. Even then, producing coherent structures of this size remains difficult. The probability of forming a 10 billion light-year structure under standard assumptions is effectively zero. Another issue lies in causality. Regions separated by such vast distances could not have exchanged information or influence after inflation ended. Yet the coherence of these structures implies some form of coordination. This coordination should not exist. The structures also challenge how cosmic averages are defined. If structures exist at these scales, then the universe may not reach statistical uniformity within the observable horizon. This undermines the assumption that any sufficiently large volume is representative of the whole. That assumption is used everywhere, in calculating expansion rates, interpreting redshifts, and comparing distant observations. If it fails, many conclusions drawn from large-scale measurements must be re-examined. The existence of these giant structures is not a marginal problem. It strikes at the foundation of how cosmology interprets data. The cosmic web was expected to dissolve into randomness. Instead, it extends farther than theory allows, forming walls and concentrations that stretch across the universe itself. These structures were not predicted. They were not required. They were discovered accidentally, revealed only because surveys became deep and wide enough to expose them. Once seen, they could not be unseen. The universe, mapped at its larger scales, does not look like a system approaching uniformity. It looks like a place where structure persists far beyond theoretical limits, where matter remains organized across distances that should have erased all patterns long ago. And the data shows this organization clearly, repeatedly, and without regard for what cosmology expected to find. Quantum mechanics versus gravity. At the deepest level, modern physics rests on two frameworks that are both extraordinarily successful and fundamentally incompatible. Each one describes reality with astonishing accuracy, but only within its own domain. When pushed toward the same extreme conditions, they refuse to work together. This fracture does not appear in everyday experience or even most laboratory experiments. It emerges only at the most extreme scales imaginable, where the universe becomes both incredibly small and unimaginably massive at the same time. On one side is quantum mechanics, the rulebook governing particles, fields, and forces at microscopic scales. On the other is general relativity, Einstein's theory describing gravity as the curvature of space-time itself, dominating the behavior of stars, galaxies, and the universe as a whole. Each theory has been tested relentlessly and confirmed with extraordinary precision. Yet when they are forced into the same physical regime, the mathematics collapses into contradiction. Quantum mechanics is built to describe a universe that is discrete, probabilistic, and uncertain. Particles do not have precise positions and velocities at the same time. Energy comes in quantized packets. Fields fluctuate constantly, even in what appears to be empty space. At the smallest scales, reality behaves less like solid objects moving along predictable paths and more like a restless sea of probabilities governed by wave functions and operators. General relativity, by contrast, describes a universe that is smooth, continuous, and geometric. Space and time are woven together into a four-dimensional fabric that bends in response to mass and energy. Gravity is not a force acting between objects. It is the result of space-time curvature guiding the motion of matter and light. This framework excels at describing planets, black holes, gravitational waves, and the expansion of the universe itself. The problem appears when both theories are applied to the same extreme conditions. Take black holes. According to general relativity, a black hole forms when enough mass collapses into a small enough volume, creating a region where space-time curvature becomes infinite at the center, a singularity. Quantum mechanics cannot handle infinities. When quantum effects are calculated near a singularity, the equations produce meaningless results. Physical quantities blow up, probabilities stop behaving sensibly, and predictive power disappears. At the opposite extreme is the early universe. At the very beginning, all matter and energy were compressed into a tiny, incredibly dense state. Gravity was immense. Quantum effects were unavoidable. Yet applying general relativity alone produces a singularity at the Big Bang, while applying quantum mechanics alone ignores gravity entirely. Neither framework can describe that moment consistently. This incompatibility is not philosophical, it is mathematical. The equations simply do not align. Quantum mechanics treats forces as fields operating within spacetime. General relativity treats spacetime itself as dynamic. When physicists attempt to quantize gravity to describe spacetime using the same rules as quantum fields, the calculations spiral out of control. Infinite corrections appear at every step. The theory becomes non-renormalizable, meaning it cannot be adjusted to produce finite, testable predictions. This failure does not appear with the other fundamental forces. Electromagnetism, the weak force and the strong force all fit comfortably within quantum field theory. Gravity alone resists this treatment. Its geometric nature makes it fundamentally different from forces that act within spacetime rather than shaping it. The conflict becomes most apparent at the Planck scale, where distances shrink to about 10 to the power of -35 meters, and energies reach levels far beyond any particle accelerator. At this scale, spacetime itself is expected to fluctuate violently. Quantum uncertainty applies not just to particles, but to space and time. General relativity, which assumes smooth spacetime, breaks down completely. At these scales, the familiar concepts of distance, duration, and location lose meaning. Quantum mechanics demands uncertainty. Gravity demands geometry. The two demands cannot both be satisfied using existing frameworks. For decades, this conflict remained largely theoretical because experiments could not reach the necessary extremes. The Planck scale is far beyond direct experimental access. However, physics does not wait patiently for perfect conditions. Instead, it searches for indirect evidence, subtle effects where the two theories might overlap. One such overlap occurs near black hole horizons. While singularities are hidden behind event horizons, the region just outside them is extreme enough to test both gravity and quantum effects. This is where predictions like Hawking radiation emerge. According to quantum mechanics, particle-antiparticle pairs constantly form near the horizon. One can fall in while the other escapes, causing the black hole to lose mass over time. Hawking radiation exposes a deep conflict. General relativity predicts that information falling into a black hole is lost forever. Quantum mechanics forbids information loss. This contradiction is not cosmetic. It breaks one of the most fundamental rules of quantum theory. The resulting black hole information problem remains unresolved despite decades of work. Another testing ground lies in cosmic inflation. During the universe's earliest moments, quantum fluctuations were stretched to astronomical scales, seeding the structures seen today. These fluctuations are quantum in origin, but shaped by gravity. Measurements of the cosmic microwave background carry imprints of this process. Subtle anomalies, unexpected correlations, and deviations from perfect randomness hint that current models may be incomplete. Physicists also probe the overlap through gravitational waves. Detected directly for the first time in 2015, these ripples in spacetime confirm predictions of general relativity under extreme conditions. As detectors grow more sensitive, they begin probing regimes where quantum effects may subtly influence spacetime behavior. Any deviation from classical predictions would signal new physics. Laboratory experiments are also pushing boundaries. Precision measurements of atomic behavior in gravitational fields test whether quantum systems obey gravitational principles exactly as predicted. Experiments with cold atoms, interferometry and superposition under gravity are attempting to reveal whether gravity itself must be quantized or whether it behaves differently from other forces. On the theoretical front, multiple frameworks attempt to bridge the gap. String theory replaces point particles with vibrating strings, smoothing out infinities by spreading interactions across tiny lengths. Loop quantum gravity attempts to quantize spacetime itself, turning geometry into discrete units. Effective field theories treat gravity as an approximation valid up to certain energies. None of these approaches has yet produced experimentally verified predictions. The absence of experimental confirmation is not due to lack of effort. It reflects the sheer difficulty of accessing regimes where quantum gravity effects become measurable. The universe itself becomes the laboratory. Astrophysical observations, cosmological surveys, and high-energy cosmic events are studied for signs of breakdown in existing laws. The conflict between quantum mechanics and gravity also surfaces in attempts to understand dark energy and vacuum energy. Quantum field theory predicts an enormous energy density for empty space. General relativity interprets energy density as curvature. When the quantum prediction is inserted into Einstein's equations, the resulting expansion rate is catastrophically wrong. The mismatch is not small. It is off by orders of magnitude beyond comprehension. This vacuum catastrophe is another sign that the two theories speak fundamentally different languages. Quantum mechanics sees empty space as active and energetic. General relativity sees space-time responding to energy smoothly. The combination produces nonsense. As experiments push deeper into extreme regimes, the cracks become more visible. High-energy cosmic rays, early universe measurements, precision timing near massive objects, and quantum experiments under gravitational influence all explore the boundary where known physics falters. At everyday scales, the universe behaves predictably. At extreme scales, it exposes the limits of understanding. Quantum mechanics and gravity do not simply disagree. They describe incompatible versions of reality. One demands uncertainty, discreteness, and probability. The other demands continuity, geometry, and determinism. Where they overlap, physics does not merely struggle, it breaks. And it is at these breaking points, in black holes, in the earliest moments of the universe, in the structure of space-time itself, that modern physics confronts the possibility that its most trusted frameworks are incomplete, not because they fail individually, but because they cannot coexist under the same extreme conditions. Unexpected particle behavior. At the smallest scales ever probed, where particles flicker in and out of existence and forces operate over distances far smaller than an atom, physics is supposed to be at its most reliable. The standard model of particle physics was built for this domain. It catalogues fundamental particles, defines how forces act between them, and predicts outcomes with extraordinary precision. In many cases, those predictions agree with experiments to more than 10 decimal places. That precision is exactly why recent deviations have caused so much alarm. These are not dramatic failures where experiments explode or detectors malfunction. They are tiny mismatches, barely perceptible at first glance, but stubbornly persistent. When predictions are this precise, even a small discrepancy can signal something enormous hiding underneath. Two areas stand out more than any others: the behavior of the muon and subtle irregularities in the weak force. The muon looks deceptively simple. It is essentially a heavier cousin of the electron, carrying the same electric charge and spin, but about 200 times more massive. According to the standard model, muons should behave almost exactly like electrons, just scaled up in mass. That similarity makes them ideal test particles. One of the most precisely calculated quantities in particle physics is the muon's magnetic moment, often referred to as G2. This value describes how the muon wobbles when placed in a magnetic field. The wobble is influenced not just by the muon itself, but by everything else in the quantum vacuum around it. In quantum field theory, empty space is not empty. Virtual particles constantly appear and disappear, briefly interacting with real particles before vanishing again. These fleeting interactions slightly alter the muon's motion. The standard model accounts for all known particles contributing to this effect: photons, electrons, quarks, neutrinos, even the Higgs boson. The calculation is exhaustive. Decades of work went into refining it. When experiments began measuring the muon's magnetic moment with extreme precision, physicists expected near-perfect agreement. Instead, they found something unsettling. The muon was wobbling more than it should. The discrepancy was small but consistent. Early hints emerged from experiments at Brookhaven National Laboratory. Later, the muon G2 experiment at Fermilab dramatically improved precision. The result remained. The measured value did not match the standard model prediction. This mismatch suggests that unknown particles or forces may be influencing the muon. Something not included in the standard model appears to be interacting with it, altering its magnetic behavior. Because the muon is heavier than the electron, it is more sensitive to high energy effects, making it a natural probe for new physics. Physicists explored every conventional explanation. Measurement errors were scrutinized. Detector calibrations were rechecked. Theoretical calculations were refined, recalculated, and independently verified. The anomaly persisted across methods and teams. The tension lies just beyond what physicists are comfortable dismissing as noise. If the anomaly is real, it implies the presence of new particles, possibly undiscovered bosons, hidden dimensions, or interactions that only reveal themselves through subtle quantum effects. These particles would not appear directly in detectors, but their influence would be felt through precise measurements, like G2. The muon, expected to be boring, became a messenger. Weak force irregularities. The weak force governs radioactive decay and particle transformations. It is responsible for processes like beta decay, where one type of particle turns into another. The standard model describes the weak force using well-defined rules, including a principle known as lepton universality. Lepton universality states that the weak force should treat all leptons, electrons, muons, and tau particles in the same way, aside from differences caused by their masses. In other words, the probabilities of certain decay should be predictable once mass differences are accounted for. This expectation was tested in high-energy particle collisions, particularly in experiments studying B mesons, unstable particles containing bottom quarks. When B mesons decay, they can produce different types of leptons. The standard model predicts very specific ratios for how often electrons versus muons should appear. Those ratios began to deviate from expectations. Experiments at facilities like CERN's LHCb detector observed that decays involving muons occurred less frequently than predicted when compared to those involving electrons. The effect appeared consistently across multiple decay channels and datasets. These deviations were subtle but systematic. The weak force seemed to be treating muons and electrons differently, in violation of lepton universality. This was not supposed to happen. The standard model leaves no room for such behavior without introducing new interactions. Once again, experimental uncertainties were examined. Background noise, detector biases, and statistical fluctuations were carefully analysed. As measurements improved, the anomalies remained visible. The pattern suggested that an unknown influence was modifying how the weak force operates in certain conditions. This could point to new force-carrying particles that couple more strongly to muons than electrons, or entirely new symmetries beyond the standard model. The irregularities were not dramatic enough to overthrow the model outright, but they were too persistent to ignore. Why these hint at physics beyond the standard model? The standard model is not a flexible framework. It does not easily accommodate surprises. Its parameters are tightly constrained, and its predictions are interconnected. A deviation in one area often implies consequences elsewhere. The muon G2 anomaly and weak force irregularities share a critical feature. They both involve muons behaving unexpectedly. This convergence is difficult to dismiss as coincidence. It suggests that muons may be particularly sensitive to physics that lies outside the standard model. Crucially, these anomalies appear in precision measurements, not in high-energy collisions that produce obvious new particles. This implies that new physics might be subtle, weakly interacting, or hidden in ways current detectors cannot directly observe. Such physics could involve new force carriers with small coupling strengths, additional quantum fields influencing known particles, hidden symmetries or broken symmetries not accounted for, and particles that exist at energies just beyond current experimental reach. The Standard Model was never expected to be the final theory. It does not explain dark matter, dark energy, gravity, or why particles have the masses they do. These anomalies offer rare experimental footholds into territory beyond it. What makes them compelling is not their size, but their consistency. Independent experiments, different methods, and separate theoretical calculations all point toward the same conclusion. Something is missing. The particles behave almost exactly as expected, but not quite. And in a framework as precise as the Standard Model, not quite is often where revolutions begin. It's not one error, it's a pattern. For a long time, the anomalies were treated the way science has always treated discomforting data, as problems to be isolated. A calibration issue here, a statistical fluctuation there, an outlier waiting to disappear once the dataset grew large enough. That approach worked before, many times. History rewarded caution. Most apparent crises in physics faded when instruments improved or assumptions were corrected. But this time, something different began to happen. Instead of vanishing, the discrepancies multiplied. They appeared in unrelated corners of physics. They emerged from experiments built for entirely different purposes, using different methods, technologies, and assumptions. They came from space-based observatories and underground particle detectors, from telescopes mapping billions of galaxies, and from accelerators smashing particles together at nearly the speed of light. And slowly, reluctantly, scientists began to realize that these were not isolated mistakes. They were connected symptoms. The most unsettling feature was not the size of any single anomaly. On their own, many of them looked modest. Some were barely strong enough to raise eyebrows, but taken together across disciplines and scales, they formed a coherent picture of tension between observation and theory. The universe was behaving consistently, but not in the way the models said it should. This realization did not arrive with a dramatic announcement. It crept in through conference talks, footnotes in papers, quiet conversations between researchers comparing results that should not have agreed, yet did. Independent experiments, separated by geography, funding agencies, and scientific cultures, were pointing in the same direction. Cosmologists noticed that measurements of the universe's expansion rate depended on how and where they looked. Early universe measurements using the cosmic microwave background told one story. Late universe measurements using supernova and galaxies told another. The difference was not shrinking as data improved, it was becoming sharper. Particle physicists saw something similar. Precision measurements of particle behavior deviated slightly from predictions in ways that could not be explained by known uncertainties. These deviations appeared in experiments designed to test completely different aspects of the Standard Model. They did not cancel out. They accumulated. Astrophysicists studying large-scale structure found patterns that extended farther than theoretical limits allowed. Those studying the early universe found correlations that should not have survived inflation. Those analysing gravitational behaviour found hints that gravity might not behave exactly as expected at either very small or very large scales. What made this especially troubling was that the instruments did not talk to each other. A space telescope mapping the microwave background does not share systematic errors with a ground-based particle detector. A spectroscopic galaxy survey does not inherit biases from a muon storage ring. Gamma-ray burst detectors do not suffer from the same limitations as optical telescopes. Each experiment has its own weaknesses, its own noise sources, its own calibration challenges. Yet the tensions persisted across all of them. This is where the pattern became impossible to ignore, When an error appears in one experiment, it can be blamed on technique. When the same kind of discrepancy appears in multiple experiments using different tools, different assumptions, and different data, the explanation changes. The problem stops looking like a mistake and starts looking like a limitation of the framework being used to interpret reality. The models themselves came under scrutiny. The standard model of particle physics had always been honest about its limits. It never claimed to explain gravity, dark matter, or dark energy, but it was assumed to be internally complete within its domain. Now, subtle cracks were appearing even there. The behavior of certain particles did not quite align with predictions. The weak force showed hints of asymmetry where symmetry was expected. Precision calculations no longer landed exactly on experimental values. Cosmology faced an even deeper problem. Its standard model, lambda CDM, had been praised not because it explained everything, but because it explained so much with so little. A handful of parameters described the universe's expansion, structure formation, and large-scale behavior with impressive accuracy. But those parameters were beginning to disagree with one another depending on how they were measured. The expansion rate inferred from the early universe did not match the expansion rate measured today. The distribution of matter inferred from cosmic background radiation did not line up perfectly with the distribution seen in galaxy surveys. The behavior of dark energy appeared consistent in some observations and variable in others. Each tension, considered alone, might have been tolerable. Together, they formed a network of inconsistencies. This was not chaos, it was structure, the wrong kind. The same models were being stretched to explain phenomena across enormous ranges of scale, from subatomic particles to the observable universe. And at both ends, they were beginning to fray. What made the situation especially uncomfortable was that adding more data did not resolve the tensions. In many cases, it sharpened them. Error bars shrank. Confidence increased. Discrepancies remained. Scientists are trained to distrust patterns until they survive every attempt to destroy them. These survived. Different teams reanalyzed the same data using independent methods. Results held. Competing experiments checked one another. Signals persisted. Simulations were refined. The universe refused to cooperate. This forced a shift in mindset. Instead of asking which experiment was wrong, researchers began asking which assumptions were shared across all of them. That question led directly to the underlying models. The equations describing cosmic expansion assume a particular form of dark energy. The equations describing structure formation assume specific properties of dark matter. The equations describing particle interactions assume certain symmetries, and conservation laws hold exactly at all energies. If those assumptions are even slightly wrong, the consequences ripple everywhere. A small change in how dark energy behaves alters the universe's expansion history, which affects distance measurements, structure growth, and cosmic background signals. A small deviation in particle interactions influences precision experiments, decay rates, and magnetic moments. A breakdown in gravity at extreme scales reshapes black holes, the early universe, and cosmic structure. The anomalies did not contradict one another. They reinforced one another. This is the defining feature of the pattern scientists began to recognize. Independent experiments were not producing random failures. They were converging on the same uncomfortable conclusion. The current models work extremely well within certain boundaries, but those boundaries are real, and they are being crossed. The universe was not violating physics, it was exposing the edges of it. There was no single equation to fix, no missing constant that could be adjusted to make everything line up again. Attempts to patch one problem often worsened another. Adjusting dark energy to fix expansion tensions affected structure formation. Modifying particle interactions to explain anomalies conflicted with other precision tests. This interconnected fragility suggested something deeper than parameter tuning. It suggested that the foundational descriptions themselves might be approximations, effective theories that describe reality only within limited regimes. That idea is not new. Newton's laws were once thought universal until relativity revealed their limits. Classical electromagnetism worked perfectly until quantum mechanics exposed phenomena it could not explain. Each transition followed the same pattern. Increasing precision revealed inconsistencies, which eventually forced a deeper framework. The current situation fits that historical pattern uncomfortably well. What makes it different is scale. The inconsistencies now appear simultaneously at the largest and smallest extremes of nature. The universe, when examined in its infancy, does not align perfectly with how it behaves today. Matter, when examined at quantum scales, does not behave exactly as the standard model predicts. Space and time, when examined under extreme gravity, defy smooth description. The pattern crosses boundaries that once kept disciplines separate. Cosmology and particle physics, long treated as distinct fields, now share problems that cannot be solved independently. Dark matter appears in galaxies and particle detectors alike. Dark energy influences cosmic expansion and vacuum energy calculations. Quantum effects shape early universe structure. Gravity influences particle behavior near black holes. The models were never designed to handle this overlap fully. Scientists did not arrive at this realization through speculation or dissatisfaction. They arrived through data, through years of measurements that refused to converge, through consistency where inconsistency was expected, through agreement across experiments that had no reason to agree if the problem were merely technical. The realization was unsettling precisely because it was slow and unavoidable. There was no dramatic failure. No experiment declared the models wrong. Instead, the models began to look increasingly strained, like a map that works perfectly at city scale but distorts continents. This is why the problem is deeper than a single error. It is not one telescope misreading light, not one detector miscounting particles, not one analysis choosing the wrong statistical method. It is a pattern emerging from independent attempts to describe the same universe. A universe that appears consistent with itself, but not entirely consistent with the frameworks built to explain it. The conclusion scientists are forced toward is not that physics is broken, but that physics is incomplete. The existing models describe a portion of reality with extraordinary success, but they are not the final word. They are approximations, valid within limits, that are now being reached. And the deeper the universe is observed, the more clearly those limits reveal themselves, not as random failures, but as a coherent signal that something fundamental is missing from the picture. Not a mistake, a pattern. Modified gravity theories. When scientists began to seriously question whether gravity itself might be incomplete rather than unseen matter filling the gaps, it was not because they wanted to overturn Einstein. It was because the data refused to stay quiet. Modified gravity theories did not emerge from philosophy or speculation, but from a growing discomfort with the way the universe behaves when measured carefully. For decades, cosmology leaned heavily on the assumption that gravity, as described by general relativity, works perfectly at all scales, and that any mismatch between prediction and observation must be explained by adding new components to the universe. Dark matter and dark energy became those components. But as measurements sharpened, certain patterns appeared that could not be easily dismissed as noise or experimental error. This is where modified gravity enters the story, not as a replacement for physics, but as a response to stubborn facts. The central idea behind modified gravity is deceptively simple. Instead of assuming that gravity behaves exactly the same way everywhere, under all conditions, these theories propose that gravity may change its behavior at extremely low accelerations or over enormous distances. This idea sounds radical only because general relativity has been tested so successfully within the solar system, and around compact objects like neutron stars and black holes. But the universe at galactic and cosmic scales operates in regimes far removed from anything we can recreate locally. Galaxies rotate slowly, stars orbit in weak gravitational fields, and structures stretch across millions or billions of light years. Modified gravity theories ask whether the laws we trust so deeply have simply been extrapolated too far beyond where they were ever tested. The earliest and most influential of these ideas is modified Newtonian dynamics, known as MOND. It did not begin as a grand theory of everything, but as a precise mathematical adjustment proposed to explain galaxy rotation curves. When astronomers like Vera Rubin measured how fast stars orbit the centers of galaxies, the results consistently showed that stars far from the galactic core were moving much faster than Newtonian gravity predicted. Under standard gravity, those stars should slow down as distance increases. Much like planets in the outer solar system move more slowly than inner ones. Instead, galaxies showed flat rotation curves, where orbital speeds remain nearly constant far from the center. MOND approaches this problem by proposing that Newton's second law, or the law of gravity itself, changes when accelerations fall below a certain tiny threshold. This threshold is so small that it would never be noticeable in laboratories or planetary systems, but it becomes dominant at galactic scales. When applied, MOND reproduces observed galaxy rotation curves with remarkable precision, often using only the visible matter in the galaxy. No invisible halo of dark matter is required to make the equations work. This success is not anecdotal. Across hundreds of galaxies spanning different sizes, shapes, and compositions, MOND consistently predicts rotational behavior using a single universal acceleration scale. This consistency is unsettling for the standard cosmological model. In lambda CDM, dark matter halos must be carefully tuned to match each galaxy's visible structure. Simulations require complex feedback processes involving star formation, supernova explosions, and gas dynamics to sculpt dark matter into shapes that match observations. MOND bypasses all of that complexity with a single modification to gravity. The tight relationship observed between visible matter and gravitational effects, known as the radial acceleration relation, falls out naturally from MOND, but appears almost coincidental in dark matter models. For many researchers, this correlation feels too precise to be accidental. However, MOND is not without serious limitations. While it performs exceptionally well at the scale of individual galaxies, it struggles to explain phenomena at larger cosmic scales. Galaxy clusters still show gravitational discrepancies even under MOND, suggesting that some unseen mass or additional modification is still required. The cosmic microwave background, with its precisely measured acoustic peaks, also aligns more naturally with dark matter-based models than with MOND alone. Attempts to extend MOND into a fully relativistic framework compatible with Einstein's equations have produced theories such as TVS, but these often introduce additional fields that complicate the picture and reduce predictive power. Despite these challenges, MOND refuses to fade away because its successes are not superficial. It captures a real feature of the universe that standard gravity plus dark matter struggles to explain cleanly: the deep and consistent coupling between ordinary matter and gravitational behavior. This suggests that gravity may be responding directly to the distribution of baryonic matter in a way that general relativity does not fully capture at low accelerations. Whether this points to a deeper theory or a coincidence layered on top of dark matter remains unresolved, but the question itself has become unavoidable. Emergent gravity takes the challenge even further by questioning whether gravity is a fundamental force at all. Instead of modifying equations directly, emergent gravity proposes that gravity arises from underlying microscopic processes, much like temperature emerges from the collective motion of atoms. This approach draws heavily on developments in theoretical physics, particularly the study of black hole thermodynamics and quantum information. In these frameworks, space and time themselves may not be fundamental, but emergent properties arising from deeper degrees of freedom. One of the most prominent formulations of emergent gravity was proposed by Eric Verlinde, who argued that gravitational attraction could result from changes in entropy associated with the distribution of matter. In this picture, gravity is not a force transmitted through space-time, but a macroscopic effect of information stored on holographic screens. When applied to galaxies, emergent gravity naturally produces additional gravitational effects without invoking dark matter particles. The equations yield corrections that become important at large distances, closely resembling the behavior observed in galactic rotation curves. What makes emergent gravity particularly compelling is that it connects cosmology with quantum theory in a way that traditional approaches struggle to do. Dark matter treats gravity as fundamental and adds new particles to account for missing mass. Emergent gravity instead treats gravity as derivative, arising from the statistical behavior of microscopic information. This shift reframes the problem entirely. Instead of asking what unseen matter exists, it asks what space-time itself is made of and how its structure responds to matter and energy. Yet emergent gravity faces obstacles similar to MOND when confronted with the full range of cosmological data. While it can reproduce certain galactic-scale observations, it has difficulty accounting for gravitational lensing in galaxy clusters, where the bending of light suggests more mass than visible matter alone can provide. The cosmic microwave background also poses a challenge, as its detailed structure reflects conditions in the early universe that emergent gravity has not yet fully explained. Additionally, emergent gravity remains less mathematically developed than general relativity, with open questions about consistency, dynamics, and testable predictions. What unites MOND and emergent gravity is not that they solve everything, but that they solve some things too well to ignore. Both frameworks reproduce specific observational relationships that appear unnatural within lambda-CDM without fine-tuning. Both suggest that gravity may behave differently depending on scale or context. Both challenge the assumption that missing mass is the only reasonable explanation for cosmic anomalies. And both force physicists to confront the possibility that the universe is not merely hiding components from us, but operating under rules we do not yet fully understand. The resistance to modified gravity within the scientific community is not rooted in dogma, but in caution. General relativity has passed every direct experimental test with extraordinary precision. Gravitational waves, black hole imaging, and precision timing of pulsars all confirm Einstein's equations in extreme environments. Any alternative theory must reproduce these successes while also explaining large-scale anomalies. This is a high bar, and many modified gravity models fail when subjected to rigorous scrutiny. But the existence of failures does not erase the motivation behind the search. What has shifted in recent years is the realization that anomalies are not isolated. Galaxy rotation curves, the Hubble tension, large-scale structure formation, and potential evolution in dark energy all point toward cracks in the standard framework. Modified gravity theories offer one possible thread that could tie some of these observations together. If gravity changes subtly over cosmic distances or low accelerations, it could influence structure formation, expansion rates, and galactic dynamics simultaneously. This does not guarantee correctness, but it provides a unifying direction for inquiry. Another reason modified gravity remains relevant is that dark matter itself has yet to reveal its nature. Decades of direct detection experiments have failed to identify dark matter particles, despite increasingly sensitive instruments. While absence of evidence is not evidence of absence, The continued silence has encouraged some physicists to revisit alternatives that were once considered fringe. Modified gravity benefits from this shift, not because dark matter has been disproven, but because the universe has not confirmed it in the ways once expected. Importantly, modified gravity does not require rejecting dark matter outright. Some hybrid models propose that both effects may be present, with modified gravity operating alongside some form of unseen mass. These approaches attempt to capture the strengths of both frameworks, though they often add complexity. The broader point is that the landscape of cosmological theory is no longer dominated by a single, uncontested narrative. Multiple explanations are now being explored in parallel, guided by observation rather than preference. As telescopes grow more powerful and surveys more comprehensive, modified gravity theories are being subjected to increasingly precise tests. Weak gravitational lensing, redshift space distortions, and galaxy clustering patterns all offer ways to distinguish between modified gravity and dark matter-based models. Upcoming data will not merely refine parameters, but potentially rule out entire classes of theories. This is the environment in which MOND, emergent gravity, and related ideas must prove themselves. What these theories ultimately reveal is not yet clear, but they already demonstrate something crucial. The universe is not obligated to conform to the simplest extensions of familiar laws. It operates across scales and conditions that challenge intuition and extrapolation. Modified gravity theories exist because observations demanded them, not because scientists were searching for novelty. Whether they represent stepping stones toward a deeper understanding or detours along the way, they reflect an honest confrontation with data that does not behave as expected. Within this context, the question is no longer whether gravity might need modification, but where and how such modifications would appear. The universe has provided hints in the rotation of galaxies, the structure of cosmic filaments, and the tight coupling between matter and motion. These hints have not yet assembled into a complete alternative theory, but they persist across independent observations. Modified gravity remains one of the few frameworks capable of engaging with these patterns directly, even as it struggles to encompass the full complexity of the cosmos. The story unfolding here is not one of replacement, but of pressure. Observations are pressing against theoretical boundaries, and modified gravity theories are one response to that pressure. They show how the universe may be doing something more subtle than simply hiding most of its mass. They suggest that space-time itself could be dynamic in ways we have not fully captured, and they leave open the possibility that gravity, the force that shapes everything from falling apples to colliding galaxies, may still hold fundamental surprises at the largest scales imaginable. Early dark energy models. Early dark energy models did not appear because scientists were looking for a clever tweak to rescue an old theory. They appeared because measurements of the universe began to disagree with each other in a way that could not be ignored. The disagreement was precise, persistent, and grew sharper as instruments improved. At the center of it was the Hubble constant, the number that describes how fast the universe is expanding today. When measured using the cosmic microwave background, the expansion rate came out slower. When measured using nearby supernovae and galaxies, it came out faster. Both methods were internally consistent. Both were built on independent physics, and neither would bend enough to meet the other. This tension was not small. It was far beyond statistical noise. It survived new data releases, recalibrations, and alternative analysis methods. The universe, it seemed, was expanding at two different speeds depending on how and when you measured it. That contradiction forced cosmologists to consider a deeply uncomfortable possibility. Something happened in the early universe that standard cosmology was missing. Early dark energy models focus precisely on that window, not the present-day universe dominated by dark energy, and not the primordial instant of the Big Bang, but a narrow epoch in between, when the universe was only a few tens of thousands of years old. During this time, matter and radiation were competing for dominance, and tiny fluctuations were being frozen into the structure of the cosmos. In standard lambda CDM cosmology, dark energy is assumed to be negligible during this period. It is treated as a constant background force that only becomes important billions of years later. Early dark energy models challenge that assumption directly. The core idea is that dark energy may not have been constant at all. Instead, it may have briefly surged in strength early in cosmic history, behaving like a temporary energy field that influenced expansion and then faded away. This early burst would not dominate the universe permanently. It would rise, affect key physical scales, and then decay, leaving behind a universe that looks broadly similar to what lambda CDM predicts, but with subtle and crucial differences imprinted into its structure. These temporary energy fields are modelled using scalar fields, similar in mathematical form to those used in theories of inflation. The field remains dormant for much of cosmic history, then becomes dynamically important at a specific time, contributing a few percent of the total energy density of the universe. That percentage may sound small, but at that early epoch, even slight changes have dramatic consequences. Expansion rates, sound horizons, and the timing of matter radiation equality are all exquisitely sensitive to the energy balance of the universe at that time. What makes early dark energy especially powerful is where it acts. It modifies the universe before the cosmic microwave background photons decouple from matter. That moment, when light first travelled freely through space, sets a cosmic ruler known as the sound horizon. This ruler is used to calibrate distances across the universe. If early dark energy slightly increases the expansion rate before decoupling, it shrinks the sound horizon. That smaller ruler then propagates forward into all later distance measurements. This is where the Hubble tension begins to ease. A smaller sound horizon allows the same observed patterns in the cosmic microwave background to be consistent with a faster present-day expansion. In other words, early dark energy changes the calibration, not the late-time physics. It does not require altering supernova data or local measurements. It adjusts the early universe in a way that allows both sets of observations to coexist. Crucially, this adjustment happens without breaking the successful predictions of the standard model at later times. After the early dark energy field decays, the universe returns to behavior that closely resembles lambda CDM. Dark matter dominates structure formation. Ordinary dark energy resumes its slow acceleration. Galaxies and clusters form as expected. The intervention is brief, targeted, and invisible to most late-time observations, except through the imprint it leaves on fundamental scales. This is why early dark energy gained attention so quickly. It addressed a specific, well-defined problem using known theoretical tools. It did not require exotic new particles with arbitrary properties. It did not discard general relativity. It respected existing constraints while offering a clear mechanism for resolving a growing crisis. For a field accustomed to incremental adjustments, this was an unusually clean proposal. But the universe does not yield easily. As early dark energy models were tested against increasingly precise data, new tensions emerged. Adding energy to the early universe affects not just the expansion rate, but also the growth of structure. It influences how quickly density fluctuations evolve, how matter clusters, and how gravitational potentials change over time. These effects leave signatures in the cosmic microwave background beyond the primary acoustic peaks, particularly in polarization data and lensing measurements. Some versions of early dark energy fit the Hubble constant beautifully, but struggle to reproduce the observed amount of structure in the universe today. Others preserve structure formation, but require finely tuned parameters to avoid conflict with data. The temporary energy field must activate at just the right time, with just the right strength and decay in just the right way. Small deviations can spoil the fit. This sensitivity has raised concerns about whether early dark energy represents a physical reality or a mathematically convenient patch. Still, the models refuse to collapse under scrutiny. Refined versions introduce smoother transitions, multiple fields, or interactions that stabilize the behavior. Large collaborations have tested these models against Planck data, baryon acoustic oscillations, supernova surveys, and gravitational lensing maps. In many cases, early dark energy remains viable, neither confirmed nor ruled out, existing in a narrow but persistent region of parameter space. What makes this particularly striking is that early dark energy does not emerge in isolation. It aligns with a broader pattern in modern cosmology, where multiple independent measurements suggest that something about the early universe may be missing from the standard picture. The Hubble tension is the most visible symptom, but not the only one. Subtle discrepancies in structure growth, lensing amplitudes, and galaxy clustering all point in the same direction. Early time physics matters more than previously assumed. Early dark energy reframes the role of dark energy entirely. Instead of being a passive background that switches on late, it becomes a dynamic participant in cosmic history. This challenges the idea that dark energy can be treated as a simple cosmological constant. It suggests that the energy content of the universe may have evolved in stages, with different components dominating at different times in ways that are not captured by a single equation. This evolution does not violate known physics, but it stretches its application. Scalar fields are common in theoretical models, and nothing forbids them from behaving dynamically. What is new is the realization that such behavior may be necessary to reconcile observation with theory. The universe, once thought to follow a clean, monotonic path from radiation to matter to dark energy domination, may have experienced brief but influential detours along the way. The appeal of early dark energy lies in its restraint. It does not attempt to explain everything. It does not claim to solve all cosmological problems. It targets one specific discrepancy and offers a mechanism that can be tested, constrained, and potentially falsified. Upcoming observations, particularly from high-precision galaxy surveys and next-generation cosmic microwave background experiments, will push these models to their limits. If early dark energy exists, it will leave subtle fingerprints in the polarization of ancient light, in the distribution of galaxies, and in the way gravitational potentials evolve over time. If it does not, the tightening constraints will force cosmologists to look elsewhere. Either outcome advances understanding. What matters is that the universe has forced this line of inquiry into existence. Early dark energy models demonstrate that the universe may not have followed a single, unbroken script from the Big Bang to the present day. They show how a brief, temporary energy field could reshape cosmic measurements billions of years later. They reveal how deeply interconnected cosmic epochs truly are, where small changes in the early universe echo across time. And they underscore a growing realization in cosmology. The universe's behavior cannot always be captured by constants assumed to be eternal. Hidden dimensions and exotic fields. For decades, physicists have operated under the assumption that the universe is composed of the familiar three dimensions of space and one of time. It is a framework that has served us well, allowing for predictions of planetary motion, black holes, and the bending of light. But as observations grew more precise, cracks began to appear that suggested this four-dimensional picture might not be the whole story. Certain cosmic phenomena, from galaxy rotation anomalies to subtle deviations in particle behavior, hinted that additional factors might be influencing reality in ways that our current models cannot account for. This is where the idea of hidden dimensions and exotic fields comes into play. The concept of extra dimensions is not speculative fantasy. It is a mathematical necessity in theories like string theory. According to these frameworks, particles are not point-like, indivisible objects, but tiny vibrating strings. The vibrational patterns of these strings determine the particle's mass, charge, and interaction properties. For the mathematics of string theory to be internally consistent, the universe must have more than 4 dimensions, often 10 or even 11. These extra dimensions are not visible in everyday life because they are thought to be compactified, curled up so tightly that they are effectively hidden from ordinary observation. Yet their presence influences the behavior of particles, forces, and the very structure of space-time itself. Hidden dimensions are not merely a theoretical curiosity. They provide a mechanism that could explain why gravity is so weak compared to other forces, why dark matter behaves as it does, and why certain anomalies appear in the cosmic microwave background. In scenarios where these extra dimensions exist, gravity could leak into higher dimensional space, appearing weaker at large scales than expected. Likewise, the properties of particles, including those that influence galaxy formation or early universe dynamics, could be subtly altered by the geometry of dimensions we cannot directly see. Scalar fields are intimately tied to this picture. In cosmology, a scalar field is a quantity that has magnitude but no direction at every point in space and time, as opposed to a vector, which also has direction. The Higgs field, familiar from particle physics, is one well-known example. It provides mass to particles through its interactions. But other scalar fields could exist that interact with the universe in more exotic ways. Unlike ordinary matter or radiation, these fields could dominate cosmic evolution at specific epochs, influencing expansion, structure formation, and the behavior of gravity itself. The interplay between hidden dimensions and scalar fields opens a remarkable possibility. The effects we attribute to dark energy, dark matter, or modifications of gravity could, in principle, arise naturally from the geometry and dynamics of higher dimensional space. A scalar field embedded in a hidden dimension could appear to us as a temporary energy source, a subtle force, or a modification to known interactions. Its influence could be negligible in the early universe, surge briefly during key epochs, and fade away as the field evolves, leaving behind imprints detectable only through precise observations. One compelling aspect of this framework is that it provides explanations for phenomena that remain puzzling in conventional 4-dimensional cosmology. Galaxy rotation curves, which originally motivated MOND, could partially arise from the influence of scalar fields interacting with matter in higher dimensions. Large-scale structure anomalies, including vast filaments and walls that exceed theoretical limits, might result from subtle gravitational effects propagating through extra dimensions. Even the Hubble tension, the mismatch between early and late universe measurements of expansion, could be eased if a transient scalar field temporarily altered the expansion rate, effectively changing the cosmic ruler used to calibrate distances. In these models, the universe is not merely a collection of particles in a 4-dimensional spacetime. It becomes a dynamic, multi-layered entity where unseen dimensions and invisible fields actively shape the observable cosmos. The challenge for physicists is to translate this rich, higher dimensional mathematics into testable predictions in our 4-dimensional experience. How would we know if an extra dimension influenced a galaxy's rotation or the behavior of light from distant quasars? One approach is to look for subtle deviations from general relativity or the standard model that cannot be explained by conventional dark matter or dark energy. Precision measurements of cosmic structure, gravitational lensing, particle interactions, and even the cosmic microwave background can all contain fingerprints of these hidden components. Experimentalists are rising to this challenge. Particle accelerators probe energies where extra-dimensional effects could appear as unexpected resonances or missing energy. Astrophysicists examine the growth of cosmic structures for hints of altered gravitational behaviour. Satellite missions like Planck and upcoming observatories measure the CMB and galaxy distributions with extreme precision, capable of detecting the faint signatures of scalar fields operating across the universe. While the effects may be subtle, the cumulative evidence from multiple fronts, anomalies in particle behaviour, large-scale structure and cosmic expansion, is driving theoretical attention toward these possibilities. Crucially, hidden dimensions and scalar fields do not conflict with well-established physics. They extend it. They are not arbitrary patchwork fixes, but natural predictions of mathematically consistent frameworks designed to unify gravity and quantum mechanics. If confirmed, these ideas would represent a paradigm shift, revealing that what we perceive as the familiar universe is only a slice of a far richer reality. The anomalies that seem intractable today could then be understood as the visible manifestation of underlying processes operating in higher dimensional space. Yet, as with all cutting-edge science, the path forward is complex. Extra dimensions cannot be observed directly at human scales. Their influence must be inferred through indirect effects on known particles and forces. Scalar fields may interact weakly or transiently, making their detection extremely challenging. Theoretical models are diverse, with multiple competing predictions and significant uncertainties. Observational precision must continue improving, with overlapping methods and independent confirmation, before any claim can be accepted. Even so, the potential explanatory power is immense. Hidden dimensions and exotic scalar fields offer a unifying framework for phenomena that otherwise appear disconnected. They provide a way to address galaxy-scale anomalies, cosmic expansion puzzles, and early universe phenomena within a single theoretical structure. In a field where conventional models struggle to reconcile observations at both the smallest and largest scales, this framework presents a pathway forward, one grounded in rigorous mathematics, testable predictions, and a willingness to explore realms of reality beyond everyday perception. The universe, in this view, is far more intricate than a simple four-dimensional canvas. Its structure, behavior, and evolution may be shaped by elements we cannot directly sense, but can infer through their gravitational, energetic, and quantum fingerprints. Hidden dimensions provide the stage, scalar fields provide dynamic actors, and the observable cosmos is the projection we can study. The anomalies that defy conventional explanation may, in fact, be messages from these unseen realms, whispering the presence of a universe more complex, more layered, and more mysterious than ever imagined. Why this was accidental? Science, at its core, is a disciplined process of asking specific questions and seeking precise answers. Instruments are designed to probe particular aspects of nature, and theories are constructed to make predictions that experiments can confirm or refute. The modern era of cosmology, particle physics, and astrophysics has been defined by such careful alignment between theory, instrument, and observation. Yet, as history has shown repeatedly, some of the most transformative discoveries have arrived not because scientists set out to make them, but because the universe refused to stay quiet, revealing unexpected truths while we were looking somewhere else entirely. This is exactly what happened with the anomalies that now shake the foundations of cosmology and physics. In nearly every case, the instruments responsible for these revelations were built to confirm existing models, not to upend them. The Hubble Space Telescope, the Planck satellite, the James Webb Space Telescope, large-scale surveys like the Sloan Digital Sky Survey, particle accelerators, and underground detectors were all calibrated and optimized to test predictions derived from theories that, at the time, were considered robust. Dark matter was assumed to exist to explain galactic rotation curves, dark energy was modelled as a constant to account for accelerated expansion, and gravity was presumed to follow Einstein's equations across all scales. Scientists use these frameworks as design specifications, ensuring that the instruments would deliver measurements capable of validating or refining them. Yet the very precision that made these instruments extraordinary also made them sensitive to tiny deviations from expectations. Unexpected findings did not emerge from sloppy data, errors in measurement, or human oversight. They arose from processes that were embedded in the routine practice of science: calibration checks, data validation, and secondary analysis. While engineers were making sure instruments were functioning correctly, astronomers and physicists discovered patterns and behaviours that the instruments were never meant to detect. Subtle anomalies in galaxy distributions, discrepancies in particle behaviour, or unusual infrared signals from early galaxies appeared not in the primary mission, but as byproducts of meticulous quality control and re-examination of data. For example, in the case of the James Webb Space Telescope, its original mission was to peer into the first few 100 million years of cosmic history to confirm predictions of early galaxy formation. The expectation was that the earliest galaxies would be small, irregular, and primitive. Webb's instruments were designed to detect faint infrared signatures, allowing researchers to see back to these distant times. Yet when data were carefully calibrated and scrutinized to validate instrumental sensitivity, what emerged were massive, mature galaxies, with spiral structures and high stellar masses, existing far earlier than any theory had predicted. These galaxies were not the primary target. They were the unanticipated truth revealed because scientists ensured that every photon measured was correctly interpreted. The same pattern applies to particle physics experiments like the muon G2 study. The experiment was designed to measure a particle property with exquisite precision to test the standard model. Engineers and physicists conducted rigorous calibration and cross-checks to ensure systematic errors were accounted for. Only during this thorough process did the deviations become apparent, hinting at physics beyond the standard model. These deviations were not the object of the experiment, but they emerged as part of the careful effort to guarantee the validity of the results. Without such diligence, the anomaly might have been dismissed as noise, overlooked, or treated as an insignificant deviation. In cosmology, this same dynamic appears repeatedly. The Hubble tension did not become a crisis because someone intended to discover a conflict between early and late universe expansion rates. The difference emerged as supernova surveys, galaxy maps, and cosmic microwave background analyses refined their calibration, reduced uncertainties, and cross-checked methods. Each experiment independently pointed toward the same discrepancy. The instruments were built to measure expansion, distances, and structure formation in ways consistent with lambda CDM. Yet in the process of ensuring accuracy and reliability, they inadvertently illuminated a fundamental flaw in the underlying assumptions. This phenomenon, discoveries arising from work designed for another purpose, is a defining feature of scientific progress. It reflects the non-linear, often serendipitous nature of how knowledge expands. While textbooks and lectures present science as a tidy sequence of hypothesis, experiment, and conclusion, the historical record tells a different story. Many of the revolutions that define our understanding of the cosmos were born from accidents, coincidences, and unintended consequences. Take the discovery of cosmic expansion. Edwin Hubble did not set out to prove the universe was expanding. His early work focused on cataloguing galaxies and determining their distances using Cepheid variable stars. Only as the data accumulated and were carefully cross-checked did the redshift distance relationship become undeniable. What began as a methodical measurement process evolved into a paradigm-shattering revelation. The universe itself was stretching, contradicting centuries of static universe assumptions. Or consider the cosmic microwave background discovered by Penzias and Wilson in 1965. They were attempting to identify sources of noise in a radio antenna designed for satellite communication experiments. Their meticulous calibration work, designed to isolate and remove background interference, instead revealed a faint, persistent glow permeating the universe. The accidental detection provided a cornerstone for modern cosmology, confirming the Big Bang theory in a manner no one had initially sought. These historical parallels underscore a profound truth about scientific inquiry. Accidents drive revolutions. They arise from a combination of precision, curiosity, and diligence. Instruments and experiments are built to explore a particular domain, but when the universe misbehaves or exhibits unanticipated patterns, careful observation ensures that these deviations are noticed, analysed, and eventually understood. The discoveries of early massive galaxies, dark energy evolution, and quantum anomalies all fall into this lineage. They were accidental only in the sense that scientists were not looking for them directly, but inevitable once the universe was observed with unprecedented precision. The accidental nature of these discoveries also highlights the importance of secondary analysis. Many anomalies are first noticed not during the main data processing pipeline, but when scientists examine calibration data, control measurements, or seemingly routine cross-checks. When Webb's infrared instruments are tested for sensitivity, faint sources that should be ignored in routine analysis suddenly stand out. When Planck's detectors are recalibrated to account for thermal drift, subtle fluctuations in the CMB become statistically significant. When particle physicists analyse calibration runs or background events, deviations that were previously considered negligible emerge as potential evidence for new physics. This emphasises that science advances not only through targeted experimentation, but through rigorous attention to detail. Accidental discoveries are a testament to the meticulous nature of research. Without careful calibration, cross-validation, and secondary analysis, these anomalies would remain hidden, and the universe's secrets would continue to escape our grasp. In other words, serendipity in science is never purely chance. It is the product of preparedness, meeting opportunity, of precision tools being wielded with expertise, and of a culture of relentless verification. The pattern of accidental discovery also illustrates a broader principle. The universe rarely conforms exactly to human expectations. The assumptions built into our instruments and theories are necessarily limited by what we know and the precision we can achieve. Yet when we push instruments beyond previous boundaries to fainter signals, finer resolution, or larger volumes, the universe frequently surprises us. Early dark energy models, massive primordial galaxies, large-scale cosmic structures, and particle anomalies all represent outcomes that could only have emerged because scientists were looking closely enough to detect subtle deviations from expectations. Crucially, these accidental discoveries often force a re-examination of prior assumptions. When unanticipated phenomena appear, they not only expand our knowledge, but also expose the limitations of models, the incompleteness of theoretical frameworks, and the need for new approaches. This is why the current tension in cosmology and particle physics is not a failure of method, but a signal that our understanding is still evolving. Looking across history, it becomes clear that revolutions in science are rarely planned. They are triggered by anomalies that resist conventional explanation, by instruments that detect phenomena not explicitly sought, and by the intellectual curiosity that drives scientists to examine every detail, no matter how mundane. The expansion of the universe, the discovery of the cosmic microwave background, and the identification of previously unknown particle behaviours all arrived through such pathways. They were accidents only in the sense that scientists were not actively seeking the revolutionary truth. They were discoveries revealed because the universe itself refused to be ignored. In this context, the accidental discoveries now shaking the foundations of cosmology and physics fit a familiar pattern. Instruments like Webb, Planck, and the Large Hadron Collider were constructed to refine, test, and validate established theories. Yet in doing so, they uncovered evidence that those theories are incomplete. This is not chaos, it is the natural outcome of precision science reaching its limits. When our tools become capable of probing the universe with unprecedented accuracy, subtle contradictions that were previously invisible come to light. Science advances because of this interplay between intention and surprise. Experiments are designed with hypotheses in mind, but nature often communicates in ways that transcend those hypotheses. The careful work of calibration, data validation, and secondary analysis transforms these unanticipated signals into knowledge. Accidental discoveries are therefore not merely fortunate happenstance. They are the inevitable products of rigorous scientific practice, intersecting with a universe that refuses to follow preconceived rules. The current era, defined by tensions in the Hubble constant, anomalies in particle physics, unexpected early galaxies, and evolving dark energy, represents the continuation of this historical pattern. These findings were not sought directly. None of the instruments were built with the intention of exposing fundamental cracks in existing models. Yet because scientists approached the data with rigor, because instruments were calibrated to the higher standards, and because anomalies were investigated rather than dismissed, the universe has revealed its deeper complexity. This accidental nature does not diminish the significance of these discoveries. On the contrary, it reinforces the idea that scientific revolutions are driven as much by preparedness and diligence as by theory and design. By creating instruments capable of extreme precision and analyzing their outputs thoroughly, humanity positioned itself to witness phenomena that challenge the very foundations of knowledge. The unexpected results are a testament to both the power of modern experimental science and the subtle complexity of the cosmos itself. History teaches a clear lesson. The most profound truths are often revealed not in the act of confirming what we expect, but in the moments when reality steps outside the boundaries of expectation. The discoveries now emerging, massive early galaxies, deviations in particle behavior, anomalies in cosmic expansion, and evolving dark energy are part of this lineage. They were accidental in the sense that no one planned for them, but inevitable once the universe was observed with instruments capable of seeing the previously unseen, measured with care, and analyzed with the rigor that defines modern science. This convergence of precision, diligence, and accidental revelation is what allows science to advance. Every calibration check, every validation test, and every secondary analysis acts as a probe not just of the universe, but of our own assumptions. What emerges from these processes is not simply more data, but the opportunity to recognize patterns that defy existing models, to confront the incompleteness of our theories, and to open the door to new frameworks that might finally account for the universe in its full complexity. The accidental discoveries of today echo the accidental revolutions of the past. They remind us that progress in science is rarely linear. It is messy, unpredictable, and often born from what we were not looking for. The current anomalies, stretching from cosmic scales to subatomic realms, are the product of this same process. Instruments were designed to confirm known theories. Observations were scrutinized to ensure correctness. Data was reanalyzed to rule out error. And in the course of that rigorous work, the universe revealed behaviors that the most confident models could not predict. What happens next? The universe has spoken in whispers and anomalies so far, but the next decade promises to amplify those whispers into a roar. The anomalies that have emerged, unexpected galaxy structures, evolving dark energy, Hubble tension, and quantum particle deviations, are tantalizing hints. They point to cracks in the models we trusted for decades, but hints alone are not enough to rewrite physics or cosmology. To turn hints into certainty, the scientific community is preparing an unprecedented wave of experiments and observatories, instruments designed not merely to confirm old theories, but to confront the universe on its own terms, to test its behavior with precision beyond anything previously achieved. The Euclid telescope, scheduled for launch by the European Space Agency, is among the most eagerly anticipated. Its mission is ambitious: to map the geometry of the dark universe, tracking billions of galaxies across more than a third of the sky. Using visible and near-infrared imaging, Euclid will measure shapes, positions, and redshifts with extraordinary precision. The telescope is designed to probe the influence of dark energy and dark matter on the large-scale structure of the universe. But in doing so, Euclid may uncover patterns that contradict existing models entirely. Subtle distortions of galaxy shapes caused by gravitational lensing could reveal deviations in how gravity operates over cosmic scales. Large-scale clustering patterns might hint at hidden physics, or even suggest the influence of scalar fields or hidden dimensions. Every photon captured by Euclid is a potential messenger of phenomena we have not yet imagined. Meanwhile, the Vera Rubin Observatory in Chile is preparing to conduct the Legacy Survey of Space and Time, LSST, a decade-long project that will produce the most detailed map of the sky ever attempted. Unlike past surveys which captured snapshots, LSST will repeatedly scan the entire southern sky every few nights. This time-lapse approach allows scientists to measure the motion of galaxies, supernova, and transient events with extraordinary accuracy. By charting changes over time, researchers hope to refine measurements of the expansion rate, test early dark energy models, and detect subtle deviations in large-scale structure. The observatory's immense dataset will be analysed for patterns that may align, or conflict, with predictions of lambda CDM, modified gravity, or entirely new physics. The sheer scale and cadence of the survey make it uniquely capable of revealing phenomena that previous instruments would have missed. The Dark Energy Spectroscopic Instrument, DESI, is another cornerstone of this next wave. DESI's first results have already hinted at evolving dark energy, and the full data release promises to be transformative. By measuring the redshifts of tens of millions of galaxies and quasars, DESI reconstructs the three-dimensional structure of the universe across an enormous volume. This allows researchers to examine how cosmic expansion and structure formation have unfolded over billions of years. With this level of precision, scientists can test whether dark energy has remained constant or evolved over time, whether the cosmic web conforms to theoretical expectations, and whether gravitational laws need modification at the larger scales. DESI's spectroscopic approach, combined with massive sky coverage, enables statistical power that surpasses previous surveys, allowing the detection of subtle but systematic deviations from existing models. Adding a completely different window on the cosmos, gravitational wave cosmology is emerging as a revolutionary tool. LIGO, Virgo, and the upcoming Einstein telescope and Cosmic Explorer are no longer merely detectors of black hole or neutron star collisions. They are instruments capable of measuring cosmic distances directly. Gravitational waves travel through the fabric of space-time itself, providing an independent method to determine the expansion rate of the universe. These standard sirens could help resolve the Hubble tension without relying on electromagnetic observations, providing an entirely separate line of evidence. If the expansion rates inferred from gravitational waves differ from those obtained through traditional methods, it would dramatically reinforce the case for new physics. Yet even as these experiments prepare to collect data, scientists are mindful of the standards required to transform anomalies into accepted reality. In the past, chance fluctuations, instrumental quirks, or unrecognized biases have produced misleading results. Modern cosmology demands statistical thresholds that are extraordinarily stringent. A deviation must reach multiple sigma significance, often 5 sigma or more, before it is considered a genuine discovery. Even then, it requires replication across independent experiments to rule out systematic errors. Multiple instruments, using different methods, and observing distinct cosmic phenomena must converge on the same conclusion before a model can be considered in jeopardy. Independent verification is therefore not optional. It is essential. The history of science is littered with intriguing anomalies that disappeared under scrutiny, and the community is determined that this will not happen again. Webb's surprising galaxies, early dark energy signals, gravitational lensing anomalies, and particle physics deviations must all be reproduced, analysed, and confirmed through complementary methods. Only when multiple independent measurements agree can scientists begin to trust that the universe is truly signalling a need for a model replacement. But even independent verification is not the final step. To rewrite physics or cosmology, model replacement criteria must be satisfied. A new theory must not only explain the anomaly, it must encompass all phenomena that the previous model successfully described. Modified gravity, evolving dark energy, extra dimensions, and exotic fields may explain certain features, but they must also reproduce the successes of general relativity, the Standard Model, and lambda CDM, where these theories have been validated. This is an exceptionally high bar. It requires a theory that is more powerful, more predictive, and more internally consistent than the framework it seeks to replace. Anything less is considered an adjustment or extension, not a revolution. The upcoming experiments represent a convergence of opportunity and necessity. They are capable of generating data of unparalleled precision and volume, allowing the scientific community to confront the universe on multiple fronts. If the anomalies observed so far are genuine, these experiments may provide the independent verification required to transform hints into confirmed discoveries. If the anomalies vanish under scrutiny, the instruments will still improve our understanding of the cosmos by refining models, measuring known quantities more precisely, and testing the limits of current theories. Either outcome advances knowledge, but one outcome could rewrite everything. This is the threshold at which modern cosmology now stands. The universe has revealed cracks in our understanding, unexpected massive galaxies, evolving dark energy, tensions in expansion rates, large-scale structures beyond predicted limits, and particle behaviours inconsistent with the Standard Model. We have instruments capable of probing these cracks in unprecedented detail. The next decade promises to bring either resolution within existing models or confirmation that a paradigm shift is required. Euclid, Vera Rubin, DSEI, and gravitational wave observatories are poised not simply to refine our knowledge, but to challenge it fundamentally. The critical question is what would count as proof. Discovery in modern science is not a single measurement or a dramatic image. It is a confluence of evidence, statistically significant deviations, reproducible across independent instruments and observational methods that cannot be accommodated within current theoretical frameworks. Only when anomalies meet these rigorous standards do they compel the community to consider model replacement, to accept that dark matter, dark energy, gravity, or even the dimensions of space-time may behave in ways fundamentally different from previous assumptions.